Hello and welcome back. Tonight we're going to explore something remarkable, something that's been quietly reshaping our world while most of us sleep. We're going to talk about artificial intelligence. It's a story that spans centuries, though most people think it started just a few years ago. It involves basement experiments with vacuum tubes, mathematical breakthroughs that took 300 years to find their purpose, and mysteries we still can't quite solve. There are moments of wonder in this story, moments of strangeness, and moments that make you question what thinking really means. Before we begin, I'd love to know where you are watching from tonight. And how was your day? Drop a comment below. I always enjoy reading your comments. If you enjoy falling asleep to these videos, please consider subscribing. It helps more people find their way here. Now let's begin. In the summer of 1956, a small group of people gathered at Dartmouth College in New Hampshire for what they called a workshop. It lasted 8 weeks. Though most days only 3 to 8 people showed up. They were trying to do something that had never been done before, something that most scientists thought was either impossible or absurd. They wanted to build thinking machines. This is where the term artificial intelligence was born, not in some grand laboratory or government facility, but in a quiet academic building during summer break, with a handful of dreamers who believed that intelligence, real, genuine intelligence, could be created from scratch using mathematics and machines. Here's the detail that makes it feel real, makes it human. In that room, they kept a dictionary on a stand, and throughout those 8 weeks, people would walk up to it, flip through the pages, and look up the word heuristic. It's a word that means a practical method for solving problems. Not perfect, but good enough. It was central to what they were trying to do, and apparently not everyone knew what it meant. 50 years later, in 2006, some of those same people returned to Dartmouth for the anniversary of that workshop, and there, in that same building, was the same dictionary, still on its stand, still open to the same kinds of pages. Half a century had passed. The world had transformed. Computers had gone from room-sized machines to pocket-sized miracles. And yet, this one physical object, this paper dictionary, had remained, a quiet witness to the birth of an entire field. There's something deeply human about that image, isn't there? These brilliant minds, on the edge of creating artificial intelligence, looking up words in a paper dictionary. No internet, no smartphones, just paper and ink and ideas. They didn't know, couldn't know what they were starting. They thought, genuinely believed, that within a single generation, they'd have machines as intelligent as humans. They were wrong about the timeline, of course, wildly wrong. Artificial intelligence would take decades longer than they imagined, would hit dead ends and false starts, would require computing power they couldn't fathom, and insights that hadn't been discovered yet. But in that small room, with that dictionary on its stand, they planted a seed. They gave it a name. They believed it was possible. And in the quiet, patient way that difficult ideas grow, they were right. The name itself, artificial intelligence, captures something both ambitious and uncertain. Artificial, made by humans, not natural. Intelligence. That elusive quality we recognize but struggle to define. Put them together and you have a kind of beautiful paradox. We're trying to create something we can't fully explain, something that might think in ways we don't quite understand. And it all started in a summer workshop where people had to look up words in a dictionary. Perhaps that's fitting. After all, understanding intelligence, whether natural or artificial, starts with understanding what we mean by the words we use. What is thinking? What is learning? What does it mean to know something? These questions sound simple, but they ripple out into deep, dark waters. The people at that workshop couldn't answer those questions completely. Neither can we, really, even now. But they took the first step. They said, let's try. Let's see if we can build a mind from mathematics. Let's see what happens when we teach sand to think. And that dictionary, patient and unchanging, watched it all begin. Before we had computers as we know them today, before silicon chips and circuit boards, before programming languages and operating systems, there were vacuum tubes. Glass bulbs filled with near nothingness, glowing softly in the dark, clicking and humming as electricity flowed through them. They were the neurons of the first electronic age, fragile and hot and hungry for power. In 1951, a young graduate student named Marvin Minsky decided to build something extraordinary in his basement. He wasn't working in a university laboratory. He wasn't funded by a government grant. He was just a curious person with an idea that wouldn't let him sleep at night. What if you could build a machine that learned? So he gathered 3,000 vacuum tubes. 3,000. Imagine them for a moment, each one the size of a small light bulb, each one generating heat, each one requiring careful wiring and placement. His basement must have glowed like a strange, technological forest. The hum of it all, the warmth, the faint smell of ozone in the air. What Minsky built was called SNARC, the Stochastic Neural Analog Reinforcement Calculator. The name doesn't matter so much. What matters is what it tried to do. He was attempting to simulate a neural network, an artificial brain. Those 3,000 vacuum tubes were meant to act like 40 neurons. 40 neurons. That's all. Your brain has roughly 86 billion neurons. A fruit fly has about 100,000. Minsky's machine, taking up an entire basement, consuming enough electricity to power a modern house, generating enough heat to warm it in winter, could simulate 40. And yet, in its own strange way, it learned. You could set up a simple maze, a basic problem, and the machine would try different paths. When it found the right one, you'd reinforce that choice, literally with the reinforcement circuits built into the design. And the next time, the machine would be more likely to choose correctly. It wasn't thinking, not in any human sense, but it was changing based on experience. It was learning. There's something almost touching about the ambition of it. Minsky must have known, that 40 neurons weren't enough to do anything truly intelligent. The machine couldn't understand language. It couldn't recognize a face. It couldn't play chess or write a poem or do any of the things we associate with intelligence. But it could learn a maze. It could improve. It could change. And that was everything. Because what Minsky proved there in his basement with his forest of glowing tubes was that learning wasn't magic. It wasn't some mystical property that only biological things could possess. It was a process, a mechanical process, something that could, in principle, be built from scratch using the right components, arranged in the right way. The machine didn't last long. Vacuum tubes fail. They burn out one by one, and eventually you can't keep up with the replacements. SNARK, like so many early computers, exists now only in photographs and memories and technical papers. But the idea survived. The idea grew. Here's the beautiful part. Minsky's machine had less computing power than a modern digital watch. The phone in your pocket, if you have one nearby, resting on your nightstand perhaps, is billions of times more powerful than that room-sized network of tubes. Billions. And yet Minsky saw something true. He saw that if you could simulate neurons, if you could connect them in the right ways, if you could adjust those connections based on experience, you could build something that learned. He was right. It would just take more neurons than 40. Many, many more. And it would take time. Decades of time. There would be setbacks and disappointments, periods where everyone thought neural networks were a dead end, a failed dream, but the seed was planted. In a basement with vacuum tubes, with heat and light and the hum of electricity, someone built the first artificial neural network. It's strange to think about, isn't it? The birth of artificial intelligence happened in a basement, not a gleaming laboratory, not a corporate research center. A basement with a young person who had an idea and the stubbornness to try it. Maybe that's how most important things begin, quietly, in unexpected places, with someone who looks at the world and thinks, what if? What if we could teach sand to think? What if we could build a mind? Marvin Minsky would go on to become one of the founding figures of artificial intelligence. He'd co-found the AI laboratory at MIT. He'd write books, win awards, inspire generations of researchers. But it all started here, in a basement, with 40 artificial neurons made of glass and wire. And maybe, as you're drifting towards sleep, you can imagine that basement, the glow of the tubes, the warmth, the quiet hum, and one person standing there, watching a machine learn something for the very first time. That's where we began. That's where the path to modern AI first opened. Not with perfection, but with 40 neurons and a dream of more. Now we need to talk about something strange and beautiful, something that sits at the very heart of how artificial intelligence learns. It's a process that no single person fully programs, no engineer explicitly designs in all its details. It's more like growing a garden than building a machine. You set up the conditions, you provide what's needed, and then you step back and watch what emerges. Neural networks learn through billions, sometimes trillions, of tiny adjustments. Imagine a vast web of connections, artificial neurons linked to one another, each connection having a strength, a weight. Some connections are strong, shouting their signals across the network. Others are weak, barely whispering. And somehow, through adjusting these connection strengths over and over and over again, the network learns to see, to recognize, to predict, to understand. But here's what makes it remarkable. Nobody tells the network what those final connection strengths should be. Nobody sits down and programs in the exact weights that will let the network recognize a cat versus a dog, or translate English to French, or predict the structure of a protein. Instead, engineers design the architecture, the shape of the network, the number of layers, how neurons connect to one another. They choose the training data, the examples the network will learn from. They press start, and then the network teaches itself. It starts with random connections, chaos, essentially. A newborn network knows nothing, sees nothing, understands nothing. You show it an image and ask, "What is this?" and its answer is nonsense. A random guess that happens to be wrong in a very specific, measurable way. But that wrongness, that's where the learning lives. The network looks at how wrong it was. It calculates the error, the distance between its random guess and the right answer. And then, here's the remarkable part. It works backwards through all those billions of connections, figuring out how to adjust each one, just a tiny amount, to be slightly less wrong next time. Each connection gets a little nudge. Some get stronger, others get weaker. It's a process called backpropagation, and we'll talk more about its history in a moment. But for now, just feel the poetry of it. The network learns by understanding its mistakes and adjusting, one microscopic step at a time. You show it another image. It makes another guess. It's still wrong, but maybe slightly less wrong. Another adjustment, another billion tiny nudges to all those connections. Another image, another guess, another round of adjustments, millions of times, billions of times. Each example teaching the network a little more, each error guiding it closer to understanding. And gradually, so gradually you couldn't point to any single moment when it happens, patterns emerge. The network starts to get things right, first occasionally, then more often, then reliably. The random chaos of its initial connections has been sculpted, shaped by experience, into something that works, something that knows. But here's what's almost unsettling. If you looked inside that trained network, if you examined all those billions of connection weights, you couldn't tell a human engineer how to recreate them from scratch. They weren't designed. They were discovered, found through this process of trial and error, performed so many millions of times that the search space, the vast universe of possible connection patterns, got explored in ways no human mind could plan. It's a bit like evolution, in a sense. Evolution doesn't design organisms. It doesn't plan the eye or engineer the wing. Instead, through countless generations, through variation and selection, complexity emerges, forms that work, survive, and propagate. And after enough time, you have eyes and wings and brains, none of which were explicitly designed, but all of which function beautifully. Neural networks learn through a compressed, accelerated version of that process. Not generations, but training iterations. Not natural selection, but gradient descent. A mathematical process that finds the downward slope toward less error, toward better performance, and takes billions of tiny steps in that direction. And what emerges are solutions that humans didn't program, strategies we didn't teach, ways of seeing and understanding that we discover only by looking at what the network has learned. Sometimes researchers train a network to do one thing, say, recognize objects in photographs, and then discover it's learned something else along the way. It's developed internal representations of edges and textures. It's built detectors for curves and corners, for surfaces and shadows. Nobody told it to learn these things. They weren't in the training objective. But in the process of learning to recognize whole objects, the network discovered that understanding parts was useful. It built its own hierarchy of concepts, from simple to complex, each layer understanding something more abstract than the layer before. This is what makes neural networks so different from traditional programs. When you write a traditional computer program, you specify every step. If this, then that. Take this input, perform these operations, produce this output. The logic is explicit, written down, traceable. You can read the code and understand exactly what will happen. but a neural network. The code is those billions of connection weights, those numbers that were found, not written. The logic is implicit, distributed across the entire network, emerging from the collective behavior of artificial neurons, firing and connecting in patterns too complex for any human to fully trace. We've created intelligence we can observe, but can't entirely explain. We can see that it works, measure how well it performs, watch it solve problems we gave it. But if you ask exactly how, which specific patterns of activation, which precise sequences of calculations led to this particular answer, the network itself can't tell you, and neither can its creators. The knowledge is there, embedded in those connections, but it's not knowledge we can easily read out or translate into human terms. It's like asking someone how they recognize their mother's face. You just know. You see the face, and something in your brain, some pattern of neural activation too complex to verbalize, says mother. You didn't learn this through explicit rules. The eyes are spaced this far apart. The nose has this particular shape. You learned through experience, through thousands of glimpses, through a process your conscious mind can't access or explain. Neural networks work the same way. They know without knowing how they know. They've learned without being taught in the explicit sense. And somewhere in those billions of tiny adjustments, in that vast space of possible connection patterns, they found solutions that work. Perhaps that's what learning really is, at its core. Not following instructions, but discovering patterns. Not being told what to do, but figuring it out through experience, through countless attempts, through errors that teach you what doesn't work until you stumble upon what does. And if that's true, then maybe neural networks are learning in a way that's not so different from how you learned, how any biological brain learns. Not through programming, but through living, through trying and failing and trying again, until, gradually, the world starts to make sense. The engineers provide the structure, the data, the goal. But what emerges, the specific solution, the particular way the network comes to understand its task, that's something the network discovers on its own. It's beautiful, in a way. We've built systems that surprise us, that solve problems in ways we didn't anticipate, that develop capabilities we didn't explicitly design. We've created something that learns, genuinely learns, through a process that mirrors, at least in spirit, the way biological intelligence develops. And it all happens through billions of tiny adjustments, each one invisible, each one nearly meaningless on its own. But together, accumulated over time, they add up to something remarkable. Sometimes in science, a single paper can change everything. Not gradually, not quietly, but with the force of a door slamming shut. In 1969, that's exactly what happened to neural network research. The door didn't just close, it was locked. And most people threw away the key for more than a decade. The paper was written by Marvin Minsky. Yes, the same person who built that basement full of vacuum tubes, and his colleague Seymour Papert. It was called Perceptrons, and it was a mathematical analysis of what simple neural networks could and couldn't do. And what it proved, rigorously and undeniably, was that the simplest kind of neural network, called a perceptron, had fundamental limitations. There were basic problems it could never solve, no matter how much you trained it, no matter how many examples you showed it. The problem they focused on was something called XOR, or exclusive OR. It's a simple logical operation. The answer is yes if one input is true, but not both. True or false, but not both at once. Think of it like a light switch in a hallway with switches at both ends. The light should be on if either switch is in the on position, but not if both are on or both are off. Simple, right? For a simple perceptron, impossible. And Minsky and Papert proved it. Mathematically, elegantly, definitively. A single-layer perceptron couldn't learn XOR. It was geometrically incapable of it. Like trying to separate two intermingled groups of points with a single straight line when what you really needed was a curve. Now here's what they also said, though it often gets forgotten. They acknowledged that multi-layer networks with hidden layers between input and output, might be able to solve these problems. But they noted, nobody had a good way to train such networks. The mathematics for adjusting weights in deeper networks wasn't developed yet. Or rather, it existed, but hadn't been rediscovered in the context of neural networks. So they proved that simple networks had limits, and they noted that complex networks might work, but we didn't know how to train them properly. It was a measured, careful analysis, but the impact was devastating. Funding for neural network research dried up almost overnight. The field that had seemed so promising in the 1950s and 60s, the dream of building thinking machines from connected neurons, was suddenly seen as a dead end. If these networks couldn't even solve XOR, what hope did they have of doing anything truly intelligent? For years, decades even, neural networks were considered a failed approach. Researchers moved on to other methods, other paradigms, expert systems, symbolic AI, logic-based approaches. These became the dominant paradigms. The idea of learning from data, of networks discovering solutions through training, was largely abandoned. It's called the AI winter, a period when funding disappeared, when careers stalled, when the grand promises of artificial intelligence seemed to have been revealed as naive fantasies. And here's the tragic part, the detail that makes this story almost unbearably poignant. Frank Rosenblatt, the psychologist who had pioneered the perceptron, who had built some of the first learning machines, who had been one of the most optimistic advocates for neural networks, died in a boating accident in 1971, just 2 years after the publication of Perceptrons. He was only 43 years old. He died never knowing that multi-layer networks would eventually solve every problem Minsky and Papert identified. He died before the rediscovery of backpropagation, before the proof that deeper networks with nonlinear activation functions could, in principle, approximate any function. He died believing, perhaps, that his life's work had been proven insufficient. But he was right. His vision was correct. It just needed more layers, better training algorithms, more computing power, and more time than anyone in that era could have imagined. The solution to the XOR problem, the problem that killed neural network research for a decade, turned out to be straightforward once you had multi-layer networks and backpropagation. A network with just one hidden layer, containing just 2 neurons, could learn XOR easily, trivially even. The limitation wasn't fundamental to neural networks as a concept. It was specific to the simplest possible architecture. It's like proving that a bicycle can't climb a steep mountain and concluding that vehicles can't climb mountains, when what you really needed was a different vehicle, a car, a truck, something with an engine and gears. But for more than a decade, neural network research was frozen. Not because the idea was wrong, but because one proof of a specific limitation was taken as evidence of a general failure. The field fell silent. The papers stopped coming. The researchers moved on or gave up. And somewhere in that silence, you can almost feel the ghost of what might have been. What if Rosenblatt had lived? What if he'd been there to respond, to push forward, to advocate for deeper networks? What if the field hadn't lost one of its most passionate voices right when it needed the most? Or maybe it needed to happen this way. Maybe the technology had to catch up, the computing power, the data sets, the mathematical tools. Maybe the AI winter was necessary, a period of dormancy before the spring, but still, there's something haunting about it, a field shut down by a mathematical proof that was correct in its specifics but misinterpreted in its implications. A pioneer dying just before his vision was vindicated. A dream deferred for a generation. The irony is that Minsky himself, late in his life, expressed some regret about the impact of that book. He and Papert hadn't intended to kill neural network research. They'd intended to provide clarity, to show what simple networks could and couldn't do, to point toward what would be needed for progress. But the world heard "can't" and stopped listening. In the 1980s, researchers quietly began picking up the pieces. Backpropagation was rediscovered and applied to multi-layer networks. People started training deeper architectures, and slowly, carefully, neural networks came back from the dead. The XOR problem was solved, then harder problems, then much harder problems. Layer by layer, neuron by neuron, the field rebuilt itself from the ashes of that winter. Today, deep neural networks power much of modern AI. They recognize faces, translate languages, drive cars, discover new drugs, create art, write text. They've solved not just XOR, but problems of staggering complexity that would have seemed like magic to researchers in the 1960s. But it took time. It took patience. It took people willing to work on unfashionable ideas, to believe in a vision that had been declared dead, to push forward even when funding was scarce and criticism was abundant. And it required moving past that single proof, that one mathematical demonstration of limitation, to see the broader landscape of what was possible. Perhaps there's a lesson in that. Not every limitation is fundamental. Not every proof of can't means never. Sometimes you just need more layers, deeper understanding, better tools, and the patience to wait for technology and theory to catch up to vision. Frank Rosenblatt never got to see that vindication, but his work lived on, carried forward by others who remembered the promise of those early learning machines. And in the end, he was right. Networks could learn. They could solve complex problems. They could be the foundation of artificial intelligence. It just took an extra layer or two and 30 years of waiting. There's a moment in the history of artificial intelligence that changed everything, though it happened so quietly that most people didn't notice at the time. It wasn't a new algorithm, wasn't a breakthrough in theory. It was something simpler, more fundamental: images. Millions and millions of labeled images. Before 2009, researchers trying to teach neural networks to recognize objects in photographs had a problem. They had small data sets, thousands of images, maybe tens of thousands if they were lucky. And neural networks, it turned out, were hungry. Desperately, insatiably hungry for data. Training on thousands of images was like trying to teach someone about the diversity of life on Earth by showing them a few dozen animals. You'd get somewhere, but you'd miss so much. The nuance, the variation, the edge cases, the subtle differences that separate one thing from another. Then came ImageNet. A researcher named Fei Li, working at Princeton and then Stanford, had a vision. What if, instead of thousands of images, you had millions? What if you created a dataset so large, so comprehensive, that it could capture something meaningful about visual reality? Not everything, that would be impossible, but enough. Enough to teach a machine what a dog looks like in all its variations. Not just one dog, not a dozen dogs, but thousands of dogs in different poses, different lighting, different contexts. Enough to show what makes a chair, whether it's wooden or metal, antique or modern, photographed from above or below or the side. Building ImageNet took years. It required organizing images into thousands of categories, each one carefully defined. It required labeling. Human beings, many thousands of them, looking at images and saying, yes, this is a husky, or no, this is a Malamute, or this is a German Shepherd. The detail had to be precise. The scale had to be massive. When they were done, ImageNet contained more than 14 million images, organized into more than 20,000 categories. 14 million. It was, at the time, almost absurdly large. Who could possibly need 14 million labeled images? As it turned out, everyone who wanted to build modern AI. In 2012, a research team used a deep neural network, deeper than most people had dared to try before, and trained it on ImageNet. The network was called AlexNet, after Alex Krizhevsky, one of its creators. It had about 60 million parameters, those adjustable connection weights we talked about earlier. And it was trained on those millions of images, each one teaching the network a little more about what the visual world looks like. When they tested AlexNet in the ImageNet Large-Scale Visual Recognition Challenge, a competition to see whose system could most accurately identify objects in photographs, it won. And it didn't just win. It crushed the competition. It reduced the error rate by more than 10 percentage points compared to the second-place finisher. In a field where progress was usually measured in fractions of a percentage point, this was an earthquake. Suddenly, everyone could see what large-scale deep learning could do. Not theoretically, not eventually, but right now, with current technology. If you had enough data and enough computing power, and ImageNet provided that data. Here's what researchers discovered. Neural networks trained on ImageNet didn't just learn to recognize the specific objects in those 14 million images. They learned something deeper, more fundamental. They learned to see. The early layers of these networks developed detectors for edges, horizontal lines, vertical lines, diagonals, curves. The middle layers learned to recognize textures, patterns, simple shapes. The deeper layers learn to recognize parts of objects, eyes, ears, wheels, windows. And the final layers learn to recognize whole objects, complete concepts. This hierarchy of understanding, from simple to complex, emerged naturally from training on enough data. Nobody programmed in first look for edges, then look for shapes, then look for parts, then recognize objects. The network discovered this strategy on its own, because it's what works, it's what's efficient. It's remarkably similar to how biological vision systems in animals are organized. And once you had a network trained on ImageNet, you could use it for other tasks. You could take those learned features, those millions of connection weights that encoded knowledge about edges and textures and shapes, and apply them to new problems. Diagnosing diseases from medical images, identifying plant species, recognizing faces, analyzing satellite photographs. It's called transfer learning, and it works because the fundamental features of vision, what makes an edge, what constitutes a texture, are the same across different tasks. A network that's learned to see through training on ImageNet has learned general visual concepts that apply almost everywhere. Before ImageNet, before this availability of massive, carefully labeled data sets, neural networks were like students trying to learn about the world while locked in a small room with a handful of books. They could learn something, but their understanding was limited, narrow, prone to gaps and misconceptions. After ImageNet, after the demonstration that massive datasets enabled dramatically better performance, the door opened. Not just a little, it flew off its hinges. Companies and research labs rushed to create large datasets for everything. For speech recognition, for translation, for text understanding, for video analysis. The lesson was clear. If you want neural networks to truly learn, you need to show them the world in all its vast diversity. And that requires data. Lots of it. More than seems reasonable. More than you can easily collect. But enough to capture the patterns that matter, the variations that exist, the edge cases that reveal the boundaries of concepts. There's something almost biological about it. A human child, learning to understand the world, sees thousands of examples of common objects. They hear hundreds of thousands of sentences. They experience the world in all its richness and complexity. And somehow, through all that experience, they extract the patterns that matter. They learn what a dog is, not from a definition, but from seeing dogs. Many dogs. Different dogs. Dogs in motion and dogs asleep. Dogs barking and dogs silent. Dogs in sunshine and dogs in rain. Neural networks, it turns out, learn the same way. Not from definitions or rules, but from examples. Lots and lots of examples. ImageNet provided those examples for vision, and in doing so, it transformed artificial intelligence from a field of limited, narrow systems that could barely recognize anything reliably into a field of powerful, general systems that could see and understand visual information with something approaching human accuracy. Fei-Fei Li talks about the creation of ImageNet as being inspired by a fundamental insight, that intelligence in children emerges from rich sensory experience. A child learns about the world by seeing it, touching it, interacting with it, not by being programmed with facts, but by experiencing reality in all its complexity. If artificial intelligence was going to truly learn, it needed that same richness of experience. It needed to see millions of examples, to encounter the world in all its variations, to build understanding not from rules handed down, but from patterns discovered in data. ImageNet was that world. Those 14 million images were a kind of compressed reality, a representation of visual experience, dense enough to teach machines to see. And it worked, better than anyone expected. The networks trained on ImageNet didn't just memorize those specific images. They learned general principles of vision, concepts that transferred to new images they'd never seen before. They learned, in a meaningful sense, what seeing means. It's worth pausing on that thought as you drift toward sleep. We built artificial systems that learn to see by showing them the world. Not by programming vision, not by writing down rules about what makes an object recognizable, but by letting networks experience millions of examples and discover the patterns themselves. We gave them data, vast amounts of it, and they extracted understanding. They found, in those billions of pixels, the structure that underlies visual reality. They learned that edges matter, that textures carry information, that objects have parts, that context provides clues. They learned the way a child learns, the way any biological system learns, through experience, through seeing the world again and again until the patterns become clear. And that moment when the scale of data crossed some invisible threshold and networks suddenly learned to see with real competence, that was when modern AI truly began. When we realized that if you build the right architecture and show it enough of the world, something remarkable emerges. Not just memorization, not just pattern matching in some trivial sense, but genuine understanding, functional knowledge, the ability to recognize and classify and make sense of new things never before encountered. ImageNet was a gift to the field of artificial intelligence, a carefully curated, painstakingly labeled window into visual reality, large enough that machines could learn to see through it. Sometimes the most important discoveries are made twice, or 3 times, or more. They emerge, get lost, resurface centuries later in a completely different context, and finally find their purpose. The algorithm that enables modern neural networks to learn, the mathematical procedure that makes all of this possible, is one of those discoveries. And it has a history that spans more than 300 years. The story begins improbably in the 17th century with Gottfried Wilhelm Leibniz. You might know him as one of the inventors of calculus, working independently around the same time as Isaac Newton, sparking one of history's great scientific rivalries. But among Leibniz's many contributions to mathematics was something he called the chain rule. The chain rule is a method for taking derivatives of composite functions. If that sounds technical, abstract, like something that belongs in a dusty mathematics textbook rather than a bedtime story, well, you're not wrong. But stay with it for a moment, because there's beauty here. Imagine you have a function within a function within a function, like nested boxes, each one containing the next. The chain rule tells you how to calculate how changes in the innermost box affect the outermost one. You work backward, layer by layer, calculating how each level responds to changes in the next. Leibniz discovered this in 1673. He published it, used it, taught it to his students. It became a standard tool in calculus, taught to mathematics students for centuries. A useful technique for solving certain types of problems. Important, certainly, but not particularly remarkable. Just one more theorem in the vast landscape of mathematical knowledge. For 300 years, the chain rule lived quietly in mathematics textbooks. Generations of students learned it, applied it to physics problems and engineering calculations, and moved on. It had its uses. It was good at what it did, but it was just mathematics, abstract manipulation of symbols, a tool without a clear purpose beyond the problems mathematicians invented for each other. And then came neural networks. Remember what we said about how networks learn? They make a guess, calculate how wrong they are, and then adjust their billions of connection weights to be less wrong next time. But how do they know which weights to adjust, and by how much? How does the network figure out which connections were responsible for the error? This is where the chain rule becomes magic. A neural network is, mathematically, a function within a function within a function. Input enters the first layer, gets transformed, passes to the second layer, gets transformed again, passes to the third layer, and so on, until finally an output emerges at the end. Many layers, many transformations, each one nested inside the next. When the network makes an error, we need to figure out how each connection weight contributed to that error. We need to trace the error backward through all those layers, figuring out how the mistake at the output relates to the weights at each earlier stage. And the chain rule tells us exactly how to do that. It works backward through the network, layer by layer, calculating how the error at the output relates to the values in the last layer, then how those relate to the values in the second to last layer, then the third to last, and so on, all the way back to the beginning. At each step, the chain rule lets us calculate how much each connection weight contributed to the error. And once we know that, we can adjust those weights in the right direction, strengthening some connections, weakening others, nudging the entire network toward better performance. This process, using the chain rule to propagate error information backward through a neural network, is called backpropagation. And it's the reason modern deep learning works. Without backpropagation, you couldn't train deep networks efficiently. You'd be fumbling in the dark, trying random adjustments, hoping to stumble onto something that worked. With backpropagation, you have a systematic method, a way to learn from errors, to improve methodically, to climb toward better performance step by step. The mathematics of backpropagation was rediscovered multiple times in the 20th century. In different contexts, by different researchers, it kept appearing. Sometimes it was called the reverse mode of automatic differentiation. Sometimes it had other names, but the core idea, using the chain rule to propagate error signals backward through a network, remained the same. In the 1960s, it was discovered. In the 1970s, again. In the 1980s, researchers rediscovered it once more, and this time, finally, it stuck. A paper by Rumelhart, Hinton, and Williams in 1986 popularized backpropagation for neural networks, showing clearly how it could be used to train multi-layer networks, solving exactly the problem that had seemed insurmountable in the 1969 Perceptrons book. And suddenly, the door that had been slammed shut opened again. Multi-layer networks weren't just theoretically possible. They were practical. You could train them. You could make them learn. The AI winter began to thaw. But here's the thing that makes this story almost cosmic in its scope. Leibniz discovered the mathematical foundation for training neural networks in 1673, 3 centuries before we had computers. 3 centuries before we had any conception of artificial neural networks, or machine learning, or artificial intelligence. He discovered a tool and had no idea what it would eventually build. It's like finding a key centuries before the lock exists, or drawing a blueprint for something that won't be invented for 300 years. The mathematics was there, waiting, patient, universal, true in the 17th century and true in the 21st, describing relationships that exist independent of time or context. And when we finally needed it, when we finally built systems complex enough to require it, the tool was there, waiting in mathematics textbooks, ready to be repurposed, reinterpreted, applied to a problem Leibniz could never have imagined. There's something profound about that, isn't there? The universe handed us the solution centuries before we knew we had a problem. The mathematics of change, of nested functions, of working backward through layers of transformation, it was always there, woven into the fabric of mathematical reality. We just had to build the right kind of system to need it. Leibniz died in 1716, largely forgotten, isolated from the scientific community. His many contributions underappreciated in his lifetime. He never knew about computers, never imagined artificial intelligence, never conceived that his chain rule for calculating derivatives would one day be the engine that drives machines to learn. But his work lived on, preserved in books, passed from generation to generation, waiting for the moment when humanity would build thinking machines and need exactly the tool he'd provided. Sometimes when you're learning calculus, when you're working through the chain rule in a mathematics class, it can feel abstract, pointless even, just symbol manipulation, just exercises on a page. Why does this matter? When will I ever use this? And the answer, it turns out, is when you want to teach a machine to see, when you want to build artificial intelligence, when you want to create something that learns from experience and improves over time. The chain rule is the mathematical heart of backpropagation, and backpropagation is how neural networks learn. Every image recognized, every sentence translated, every game won, every protein structure predicted. All of it depends on mathematics discovered in 1673 by a man who could never have known what his work would enable. There's a certain poetry to that, a connection across centuries. Leibniz and the modern AI researcher, separated by 300 years, working on the same mathematics for completely different purposes, united by the timeless truth of mathematical relationships. The universe is like that sometimes, full of connections we don't see at first, tools that exist before we know what to build with them, answers waiting patiently for us to ask the right questions. And perhaps, as you're drifting off to sleep, you can imagine that continuity. Leibniz in his study, candlelight flickering, working through the calculus of nested functions, discovering something true. And centuries later, researchers training neural networks using that same mathematics, perhaps not even knowing its full history, but building on foundations laid so long ago. Knowledge builds on knowledge. Understanding accumulates across time. And sometimes the tools we need most are already there, waiting in the structure of mathematics itself, patient and eternal, ready for the moment when we finally know what to build. The chain rule was always true. It's been true since mathematics itself came into being, since the relationships it describes became part of the logical structure of reality. But it took us 300 years to build something that needed it in quite this way. And now, every time a neural network learns, billions of times per second, across millions of machines around the world, the chain rule is there, working backward through layers, calculating gradients, enabling learning. Now we need to talk about something unsettling, something that reveals just how differently neural networks see the world compared to us. It's called adversarial examples, and when researchers first discovered them, it fundamentally changed how we think about what these systems understand. Imagine you have a photograph of a panda, a cute, perfectly ordinary panda sitting there, maybe munching on bamboo. You show this image to a state-of-the-art neural network trained to recognize animals, and it confidently tells you, panda. It's correct. The network has seen thousands of pandas during training, and it knows what a panda looks like. Now, a researcher takes that same image and adds noise to it. Not random noise, carefully calculated noise, specially designed for this particular image and this particular network. The noise is tiny, imperceptible to human eyes. If you looked at the original image and the modified one side by side, you genuinely couldn't see any difference. The changes are so small, they're below the threshold of human perception. To you, to anyone, it's still just a picture of a panda. But you show this modified image to the neural network, and something strange happens. The network looks at it and confidently declares, gibbon. Not a panda, a gibbon, a completely different animal. And the network isn't uncertain about this. It's often more confident about the wrong answer than it was about the right one. This is an adversarial example, an image that's been subtly modified in ways invisible to humans, but that completely fool the neural network. When this phenomenon was first discovered around 2013, it shocked the research community. These were networks that could recognize images with near-human accuracy. They'd been trained on millions of examples. They performed brilliantly on standard tests. And yet, they could be completely fooled by changes so subtle you literally couldn't see them. It gets stranger. You can create adversarial examples that fool multiple networks at once. You can even create universal adversarial perturbations, patterns of noise that when added to almost any image will cause a network to misclassify it, like a magic spell that makes networks blind, unable to see what's actually there. Or you can go the other direction. You can create images that look like random noise to humans, just static, visual nonsense, but that the network confidently identifies as meaningful objects. This is definitely a school bus, the network says, looking at what appears to you as pure television static. What does this mean? What does it tell us about what neural networks actually understand? It suggests that networks see the world through dimensions we don't perceive. They're sensitive to patterns in the data that have no meaning to human vision, but that, from the network's perspective, are as meaningful as edges and textures are to us. They've learned correlations in high-dimensional space that happen to work for normal images, but that don't correspond to anything in our intuitive understanding of what an object is. Think about it this way. When you recognize a panda, you're relying on robust, meaningful features, the black and white coloration, the round face, the way pandas move and sit and hold bamboo. These features are stable. They mean something about what a panda actually is, biologically, in the real world. But a neural network? It's just finding patterns in pixels that correlate with the label panda in the training data. Most of the time, those patterns align with the features we'd recognize. The network learns to detect black patches around eyes, white faces, certain body shapes. But it's also learning other patterns, statistical regularities in how pixels tend to be arranged when an image happens to contain a panda. Some of these patterns are meaningful and robust. Others are accidental, fragile, artifacts of the training data rather than facts about pandas. And because the network is searching in a much higher dimensional space than we can perceive, looking at relationships between pixels that our visual system doesn't track, it finds patterns we can't see. Patterns that work most of the time, but that can be exploited if you know how. The carefully calculated noise in an adversarial example is designed to push the image across a decision boundary in that high dimensional space. To us, the image barely changes. We're only seeing 3 dimensions, essentially: the spatial layout and colors of pixels. But to the network operating in a space with thousands or millions of dimensions, the image has moved dramatically. It's crossed from the panda region to the gibbon region, even though it's barely moved at all in the dimensions we care about. It's a bit like, imagine you're navigating by visible landmarks. You know where you are because you can see the mountains, the river, the town. Someone moves you 3 feet to the left. You barely notice. You're still in the same place, essentially. But imagine there's also an invisible magnetic field, and your compass is following that instead of the landmarks. Those 3 feet might have carried you across a magnetic boundary, from one zone to another, and your compass now points in a completely different direction, even though, from your perspective, nothing has changed. Neural networks are following patterns we can't directly perceive, navigating by dimensions we don't see, and adversarial examples exploit that gap between their perceptual space and ours. This has practical implications, some of them worrying. If you can fool a neural network with imperceptible changes, what does that mean for systems that rely on these networks? Self-driving cars that might misidentify stop signs, security systems that might be tricked, medical diagnostic systems that might be fooled by carefully crafted modifications to scans. Researchers are working on making networks more robust, more resistant to adversarial examples. But it's challenging because the vulnerability seems fundamental to how these systems learn. They're optimizing to perform well on the training distribution, the kinds of images they've seen before. They develop internal representations that work for normal cases. But the space of possible images is vast, and adversarial examples exist in weird corners of that space that the network never encountered during training. It's like the network has learned a map of the territory it's seen, but there are regions of the map very close to known territory where the labels are wrong, where the network's understanding breaks down in ways it can't detect. And yet, here's the truly unsettling part. Humans have adversarial examples too. There are optical illusions that completely fool our visual system. There are perceptual tricks that make us see things that aren't there, or fail to see things that are. Our vision is also based on pattern recognition, on expectations and predictions, on shortcuts that work most of the time, but can be exploited. The difference is that our adversarial examples tend to require more obvious manipulations. The impossible triangle, the dress that looks blue and black to some people and white and gold to others. Camouflage that takes advantage of how our brain segments objects from backgrounds. Neural networks have adversarial examples that are invisible. Their illusions are subtler than ours, operating in dimensions we can't access. It makes you wonder, what is vision really? What does it mean to see something, to recognize it? Are we actually perceiving reality as it is, or are we also just finding patterns in high-dimensional sensory data, patterns that usually work but that could, in principle, be fooled. Maybe the adversarial examples aren't revealing a flaw unique to artificial networks. Maybe they're revealing something fundamental about perception itself. All seeing is interpretation. All recognition is pattern matching. And patterns can be manipulated if you know which dimensions matter to the observer. The network looking at that adversarially modified panda is having an experience we can't share. From our perspective, it's clearly wrong. That's obviously still a panda. But from the network's perspective, operating in its high-dimensional space, the image has genuinely changed. The patterns it's learned to associate with gibbon are now present in ways that overwhelm the panda patterns. Who's right? We are, of course, in the sense that the image is still of a real panda, and panda is the correct label according to how humans categorize animals. But the network isn't hallucinating exactly. It's responding to patterns that really are there in the data, even if those patterns are meaningless to us. It's seeing something we don't see. Unfortunately, in this case, what it's seeing is noise, carefully constructed noise designed to hijack its perceptual system. But to the network, that noise is as real as any other feature. Perhaps adversarial examples are teaching us humility. We built these networks. We trained them. We thought we understood what they were learning. And then we discovered they see the world through alien dimensions, respond to patterns we can't perceive, and can be fooled in ways we'd never anticipated. They're not seeing the way we see. They're not understanding the way we understand. They're finding different patterns, navigating different dimensions, operating in spaces our minds can't directly access. And that raises questions we're still grappling with. If neural networks can be so easily fooled, what does that mean for deploying them in critical systems? How do we make them more robust? Can we align their perceptual space with ours? Or is the gap fundamental? Or maybe, and this is the thought to drift off to sleep on, maybe every form of perception has its blind spots, its vulnerabilities, its dimensions it can't see, and patterns it misses. Human vision is astonishingly good at what it does, but it's not perfect. It's not complete. It's optimized for survival and navigation in the three-dimensional world we evolved in, but it's not perceiving objective reality in full. Neither are neural networks. They're perceiving patterns in data, patterns that correlate with outcomes, patterns that work in the distributions they're trained on. And sometimes those patterns are robust and meaningful, and sometimes they're fragile and exploitable. There's a phenomenon in neural networks that researchers discovered almost by accident, and it's one of the strangest, most thought-provoking things about how these systems learn. They called it grokking, borrowing the term from Robert Heinlein's science fiction novel Stranger in a Strange Land, where it means to understand something so deeply, so completely, that you become one with it. And the phenomenon deserves the name, because what happens is this. A neural network will train on a problem. It will see all the examples, again and again, and at some point, relatively early in training, it will memorize them. It will learn to give the right answer for every single example it's seen. Perfect accuracy on the training set. From a performance standpoint, it's done. Mission accomplished. But if you keep training it, if you don't stop, if you let it keep adjusting those billions of weights, even though it's already getting everything right, something remarkable happens. Sometimes thousands of training steps later, sometimes tens of thousands of steps later, long after it seemed like there was nothing left to learn, the network suddenly understands. Its performance on new examples it's never seen before, suddenly jumps. It goes from memorization to generalization, from knowing the specific answers to understanding the underlying pattern. And you can watch it happen, this sudden phase transition from a network that simply recorded the training data to a network that's grasped the concept beneath it. It's like a student who's memorized all the answers in a practice test. They can recite every answer perfectly, but they don't really understand the material. Then they keep studying, keep thinking, keep working through problems, even though they already know the answers. And suddenly something clicks. They have an aha moment. They see the pattern, the principle, the deep structure that explains why the answers are what they are. And now they can solve new problems they've never seen before because they understand rather than just remember. That's grokking. And neural networks do it. What makes it especially strange is the timing. The network has already achieved perfect performance on its training task. There's no immediate pressure to improve, no obvious error signal driving further learning. And yet, something in the training process, something about the way gradient descent works, the way those billions of tiny adjustments accumulate, pushes the network to continue searching for better solutions. Better in this case doesn't mean more accurate on the training data. It means simpler, more elegant, more generalizable. The network seems to have an implicit preference for simple solutions over complex ones. Given two sets of connection weights that both achieve perfect accuracy on the training data, the learning process naturally tends toward the simpler one, the one that captures the essential pattern rather than memorizing every detail. This is fascinating because nobody programmed that preference in explicitly. It's not like the loss function, the measure of how wrong the network is, includes a term that says prefer simple solutions. The network is just trying to minimize error, but the path it takes to minimize error, the trajectory through weight space, naturally favors simplicity. It's related to a concept in machine learning called the implicit regularization of gradient descent. Regularization is a technique where you explicitly penalize complex solutions, encouraging the network to find simple patterns. But even without explicit regularization, gradient descent seems to regularize implicitly. The way it navigates through the vast space of possible solutions tends toward elegant, general answers. And sometimes that journey takes a while. The network finds a memorization solution first, a complex, specific solution that works for the training data but doesn't generalize. And then it keeps learning, keeps adjusting, keeps searching, until it finds the deeper pattern, the simple explanation that works everywhere. Researchers have studied this most clearly in mathematical tasks, teaching networks to perform modular arithmetic, for instance, where there's a clear underlying rule. The network memorizes the specific examples. 5 plus 7 over 2 mod 10, 8 plus 4 over 2 mod 10, and so on. It can answer all the training questions perfectly, but it hasn't learned the rule, the modular structure. Not yet. Thousands of steps later, suddenly it grows. It discovers the pattern. And now it can handle any addition problem in that modular system, not just the ones it memorized. What's happening inside the network during those thousands of additional training steps? The architecture is being refined. Connections that encode the memorization solution are slowly being weakened. Connections that encode the general rule are slowly being strengthened. The network is reorganizing itself, finding a more elegant internal representation of the problem. And here's what's beautiful about it. This suggests that neural networks, in some sense, prefer understanding to memorization. Or rather, the learning process naturally drives them toward understanding when given enough time. It's not conscious, of course. The network doesn't want to understand. It's not experiencing that satisfying feeling of comprehension that we feel when something finally makes sense. But functionally, behaviorally, the outcome is similar. Given the choice between a solution that works through brute force memorization and a solution that works through elegant generalization, the network gravitates toward the latter. This has implications for how we think about learning, artificial and otherwise. It suggests that understanding isn't just more satisfying than memorization. It's also more stable, more fundamental, more aligned with the natural dynamics of learning systems. When you memorize, you're creating a fragile solution. It works for what you've seen but collapses when faced with anything new. When you understand, you found something deeper, more robust, more generalizable. And somehow, learning systems, whether biological brains or artificial networks, tend toward understanding when given enough time and the right conditions. They search the space of possible solutions and find not just any solution that works, but solutions that are simple, elegant, general. It makes you wonder about your own learning. How often have you memorized something only to later, sometimes much later, actually understand it? You knew the formula, could apply it to standard problems, but the deeper meaning eluded you. Then one day, perhaps while studying something related, perhaps while teaching it to someone else, it clicked. You grukked it. And suddenly, the formula wasn't just something to remember. It was something that made sense, that fit into a larger structure of understanding. That's the same transition the network undergoes, from knowing to understanding, from memorization to insight. The question researchers are still exploring is, why does this happen? What is it about the geometry of neural networks, about the dynamics of gradient descent, that drives toward simplicity and generalization even after accuracy is already perfect? One theory is that simpler solutions occupy larger regions of solution space. Think of it like a landscape. Complex memorization-based solutions are narrow peaks. You can stand on them, but they're small targets, easy to miss. Simple, generalizable solutions are broad plateaus. They're larger, more stable, easier to find and stay on. Gradient descent, wandering through this landscape, naturally tends toward the broader regions. Even small random fluctuations in training, different mini-batches, slight noise in the gradients, nudge the network away from narrow peaks and toward broad plateaus. Another theory focuses on the geometry of the loss surface, the shape of the error landscape that the network is trying to descend. Simple solutions correspond to flat regions where the loss doesn't change much, with small variations in weights. Complex solutions correspond to sharp regions where small changes can increase the error significantly. And there's evidence that gradient descent naturally prefers flat regions. wandering toward them even without explicit pressure to do so. Whatever the mechanism, the phenomenon is real. Networks grok. They find understanding after memorization. They continue learning even when they seem to be done. And perhaps there's a lesson in that for human learners too. Sometimes understanding comes late. Sometimes you need to keep working, keep thinking, keep engaging with material, even after you can already produce the right answers. Because there's a difference between knowing what to do and understanding why it works. And that deeper understanding, that grokking, is worth the extra time. It emerges not immediately, but gradually, through continued engagement, through allowing the learning process to refine and reorganize and simplify until the elegant pattern finally reveals itself. The network that groks has moved beyond surface-level performance to something deeper. It's found not just a solution, but the solution, the one that captures the essential structure of the problem. And in that moment of transition, invisible from the outside, marked only by improved performance on new examples, something that looks a lot like comprehension has occurred. Not consciousness, not subjective experience, but a functional kind of understanding nonetheless, a solution that works not through brute force, but through elegant generalization. The machine, in its own strange way, has understood, and it did so by continuing to learn long after it seemed there was nothing left to learn, driven by some implicit preference for simplicity, for elegance, for solutions that don't just work, but work beautifully. Perhaps that's what all learning aspires to, not just correctness, but elegance, not just answers, but understanding. And grokking is the moment when you finally get there. When researchers first started looking inside trained neural networks, really looking, trying to understand what individual neurons and layers were doing, they expected to find chaos. After all, these networks learned through essentially random initial conditions and billions of tiny adjustments driven by data. There was no blueprint, no predetermined plan, just optimization, just the blind search for weights that minimized error. And yet, what they found was structure. Beautiful, hierarchical, almost impossibly organized structure. It emerged on its own. Nobody designed it. Nobody told the network to organize itself this way. But when you train a deep neural network on visual tasks and then examine what's happening in each layer, you find something remarkable. The network has spontaneously developed an architecture of understanding that mirrors, in eerie ways, how biological vision systems work. In the earliest layers of the network, the first ones that receive the raw pixel data, neurons develop into edge detectors. Some become sensitive to horizontal edges, places where the image transitions from dark to light horizontally. Others respond to vertical edges, diagonal edges, edges at various angles. These neurons don't care about complex objects or scenes. They're looking for the most basic visual features: lines, boundaries, transitions in brightness. Nobody programmed them to do this. The network discovered, through training, that edges are fundamental, that to recognize complex objects, you first need to find their boundaries, their contours, their basic structure. Move deeper into the network, to the middle layers, and the neurons become more sophisticated. They're no longer responding to simple edges. Now they detect textures, repeated patterns of visual information. Neurons that respond to the texture of fur, or the grain of wood, or the ripples of water, or the crosshatch of fabric. Others detect simple shapes, curves, circles, corners, junctions where lines meet. These middle layer neurons are combining the edge information from earlier layers into more complex features. They're building a vocabulary of visual elements, a toolkit of patterns that appear commonly in the world. Go deeper still, and you find neurons that respond to parts of objects: eyes, wheels, windows, faces, legs. These aren't complete objects yet, but they're meaningful components, the building blocks from which objects are constructed. And in the deepest layers, the ones closest to the final output, neurons respond to whole objects and scenes. Dog neurons that activate when a dog is anywhere in the image, regardless of pose or lighting. Car neurons. Building neurons? Neurons that have learned to recognize complete, meaningful concepts. This hierarchy, from edges to textures to parts to objects, wasn't designed. It emerged. The network discovered that this is an efficient way to understand visual information. Break it down into simpler and simpler components until you reach the fundamental elements. Then build back up from those elements to complex understanding. And here's what's extraordinary. Biological visual systems work the same way. In the visual cortex of mammals, early areas like V1 contain neurons that respond to edges at particular angles. Later areas like V2 respond to more complex features, combinations of edges. Deeper still, areas like V4 respond to shapes and textures. And in high-level areas like the inferotemporal cortex, neurons respond to specific objects and faces. Evolution discovered this hierarchical architecture through millions of years of natural selection, optimizing vision systems for survival. Artificial neural networks discovered it through millions of training iterations, optimizing for accuracy on image classification. Two completely different processes. One biological, one mathematical, converging on the same solution, the same architecture, the same hierarchy of understanding. What does that tell us? Maybe that there's something fundamental about this organization, that when you're building a system to understand visual information, this hierarchical structure isn't just one possible solution among many. It's the solution, or at least something very close to it, the natural way to decompose the problem of vision. Researchers have spent countless hours visualizing what individual neurons in these networks respond to. They use techniques like feature visualization, where they ask, what input pattern would maximally activate this neuron? What is this neuron looking for? And the results are sometimes beautiful, sometimes strange, sometimes deeply revealing. You can see neurons that have learned to detect specific textures, honeycomb patterns or scales, or fur. Neurons that respond to particular colors in specific spatial arrangements. Neurons that seem to encode abstract concepts like carness or dogness, responding to many different instances of these categories, despite vast differences in appearance. Some neurons are crisp and interpretable. This one detects horizontal lines. That one responds to circular shapes. But others are more mysterious, responding to combinations of features that don't have simple names, that don't correspond to anything in our intuitive vocabulary of visual concepts. Those neurons have found patterns in visual data that are statistically useful for the network's task, but that don't map cleanly onto human categories. They're seeing structures in the high-dimensional space of images that we don't have words for, don't consciously perceive, but that exist nonetheless in the statistics of visual experience. And yet, despite these mysterious neurons, the overall organization remains clear. The hierarchy holds. Simple features build to complex features, build to parts, build to objects, each layer transforming the representation, making it more abstract, more semantic, less about pixels, and more about meaning. This emergent organization suggests something profound about learning systems. Given enough capacity, enough data, and the right objective, they don't just find solutions, they find structured solutions. They discover that organization, hierarchy, and decomposition into parts are useful. They build internal representations that make sense, that have structure we can interpret and understand. The network hasn't just memorized training images. It's learned general principles about how visual information is organized. It's discovered that the world contains edges, that edges combine into textures and shapes, that shapes combine into parts, that parts combine into objects. These are facts about the structure of reality, and the network has independently discovered them through the process of learning to see. There's something almost philosophical about that. The network's internal organization reflects the external organization of the world. The hierarchy in the network mirrors the hierarchy in reality. The fact that objects really are made of parts. Parts really are made of simpler features. Features really emerge from boundaries and transitions. The network has learned not just to classify images, but to represent them in a way that captures something true about their structure. Its internal language for describing images, the patterns of activation across layers, the features encoded in neurons, is a language that carves reality at its joints, finding the natural categories and hierarchies that exist in visual experience. And nobody taught it this explicitly. No one told the network, first find edges, then find textures, then find parts. The training objective was simply classify images correctly, minimize error, and from that simple objective, through the dynamics of learning, this entire structured architecture emerged. Its emergence in the deepest sense. The whole is more than the sum of its parts. The network's global organization, this beautiful hierarchy of understanding, isn't present in any individual neuron or connection. It's a property that arises from the collective behavior of billions of components, each one making tiny adjustments, each one responding to local information, but together creating something with coherent structure. Like how consciousness emerges from neurons in a brain, or how the behavior of a city emerges from the actions of individuals, or how the properties of water emerge from the interactions of molecules. The parts don't contain the whole, but the whole arises inevitably from the relationships between parts. The network grows itself into understanding. It starts random, chaotic, knowing nothing. And through training, through experience with data, through billions of adjustments driven by the desire to reduce error, it organizes. It structures itself. It develops this hierarchy of increasingly abstract representations that transform raw sensory data into meaningful concepts. And when you look at the final result, at the edge detectors in layer 1, the texture detectors in layer 3, the part detectors in layer 7, the object detectors in layer 10, you're seeing the fossilized history of the learning process. Each layer represents a stage in the network's developing understanding. Each level of abstraction is a plateau the network reached and built upon. It's like looking at geological strata, seeing the layers of rock that record the history of the earth, or looking at tree rings that record years of growth. The architecture of a trained network is a record of how it learned, the path it took from ignorance to understanding, frozen in the pattern of weights and connections. And that architecture, that path, leads inevitably toward hierarchy, toward decomposition, toward building complex understanding from simple foundations, because that's what works. That's what's efficient. That's what allows you to generalize, to recognize objects you've never seen before by identifying their component parts, to understand new scenes by recognizing the familiar elements they contain. The network didn't know this in advance. It discovered it. Through learning, through optimization, through the patient accumulation of small improvements, it found that hierarchical organization is the key to understanding. Just as evolution found the same solution, building biological visual systems with the same hierarchical structure through a different but equally blind process of optimization. Two paths to the same destination, two different kinds of learning, one biological, one artificial, both discovering that to understand the complex, you must first grasp the simple, and you must organize that understanding in layers, each one building on the last, each one abstracting further from raw sensation toward meaning. The network's neurons weren't programmed to detect edges or textures or parts, but they do, because in the vast space of possible solutions to visual recognition, the ones that work best, that generalize best, that are most efficient, are the ones that discover this hierarchical structure. And so almost inevitably, that's what emerges: structure from chaos, understanding from random initialization, a mirror of biological vision arising in silicon and mathematics, not because anyone planned it, but because that's where the path of learning naturally leads. When you understand how to see, this is what understanding looks like. Layers of abstraction, hierarchies of features, simple building blocks combining into complex comprehension. It's the architecture of visual intelligence. And neural networks, both biological and artificial, discover it independently when given the chance to learn. There's a particular kind of neuron that researchers discovered in advanced neural networks that shouldn't exist, or at least shouldn't exist if we understood these systems as well as we thought we did. They're called multimodal neurons, and they blur the boundaries between different kinds of understanding in ways that are both beautiful and deeply puzzling. Here's what makes them strange. Imagine a single artificial neuron, one among millions in a large network. This neuron has learned, through training, to respond to images of spiders. Show the network a photograph of a spider, any species, any pose, and this neuron activates strongly. It's become a spider detector, which makes sense. Networks learn to detect patterns, and spider-shaped things is a pattern. But then you show the network text, not images, just written words, and you include the word spider in that text, and that same neuron, the one that responds to images of spiders, activates strongly, as if it's seeing a spider even though there's no image, just letters on a screen. Or you show it an artistic drawing of a spider, highly stylized, barely realistic. The neuron activates. Or a cartoon spider, activation. Or the spider emoji, activation. Or even related concepts, words like web or arachnid or 8 legs. And you get partial activation, weaker, but definitely present. The neuron isn't just detecting a visual pattern, it's responding to the concept of spider across multiple modalities, across vision, language, symbolic representation. It somehow learned that all these different things, the sight of a spider, the word spider, the symbol, refer to the same underlying concept in the world. Nobody programmed this explicitly. The network wasn't told, make sure the same neurons respond to both images and text referring to the same thing. It discovered this on its own through training on data that included both images and their text descriptions, learning to bridge the gap between different forms of representation. And it's not just spiders. Researchers have found neurons that respond to both images of the Eiffel Tower and the text Eiffel Tower. Neurons that activate for pictures of money and financial terminology. Neurons that light up for photographs of certain celebrities and for their names written out. These multimodal neurons seem to have learned something profound, that despite the superficial differences between seeing something and reading about it, between looking at a photograph and looking at a string of letters, there's an underlying unity. They're different ways of pointing to the same thing. It's a kind of abstraction that feels almost philosophical. The neuron has moved beyond processing sensory data to representing concepts, abstract ideas that can be instantiated in multiple forms, but that have an identity that transcends any particular instantiation. When you see a spider and when you read the word spider, very different patterns of photons are hitting your retina. The visual processing is entirely different. Shapes and colors versus letter recognition and spelling. And yet somehow your brain knows these are referring to the same thing. You can read about a spider and visualize it. You can see a spider and think its name. Multimodal neurons in artificial networks are doing something similar. They're creating a shared representational space where different modalities, vision, language, symbols, converge, where the concept exists independently of its mode of presentation. This was particularly surprising because the networks that developed these neurons weren't explicitly designed for this kind of cross-modal understanding. They were trained on tasks like image classification and text processing, and the multimodal neurons emerged as a byproduct, a useful organizational principle that the network discovered on its own. It suggests that when you train a system on rich, diverse data, images with captions, photographs with descriptions, visual content paired with linguistic content, the system naturally learns to align these modalities. It discovers that there are systematic relationships between what you see and what you read, that the same underlying concepts appear in both domains, and it builds internal representations that capture those concepts in a modality-independent way. This is, in a sense, what meaning is. Not the specific sensory pattern, the particular arrangement of pixels or letters, but the concept that different patterns can point to. The spiderness that exists whether you encounter it through vision or language or symbolic notation. And somehow, neural networks trained on enough data learn to extract that meaning. They build neurons that respond not to surface features, but to deep concepts, neurons that recognize when different kinds of input are talking about the same thing. The discovery of multimodal neurons came from research into large vision language models. Systems like clip that learned to connect images and text by training on millions of image caption pairs from the internet. These models learn to place images and their corresponding text descriptions close together in an abstract representation space, while pushing unrelated images and text apart. And in the process of learning this alignment, individual neurons spontaneously develop multimodal responses. They become concept detectors that work across modalities, bridging the gap between seeing and reading, between visual recognition and linguistic understanding. It's a small miracle of learning, really. The network isn't just memorizing which images go with which captions. It's discovering the semantic structure underneath. The fact that both images and text refer to concepts, and that the same concepts can be expressed in multiple ways. When you show the network an image of a spider with the caption, "a spider," it learns something more general than just, "this image goes with these words." It learns that there's a concept, spider, that explains why this particular image and this particular text are paired. And once it's learned that concept, it can recognize it in new images it's never seen, or in text it's never encountered, or in other representations entirely. The multimodal neuron becomes a kind of concept anchor, a single point in the network's representational space that says spider, regardless of how that concept is presented. Visual input flows to this neuron through one pathway, processing edges and textures and shapes until it recognizes spider form. Textual input flows to it through another pathway, processing letters and words and meanings until it recognizes spider reference. But they converge on the same neuron, the same representation, because they're pointing to the same thing in the world. This convergence feels significant. It suggests that neural networks aren't just learning superficial associations. This pixel pattern predicts this label. That word sequence predicts that category. They're learning something deeper, something about the structure of meaning itself. They're discovering that the world has objects and concepts that exist independently of how we perceive or describe them. That a spider is a spider whether you see it or read about it. That the Eiffel Tower is the Eiffel Tower whether you're looking at a photograph or reading its name. And they're building internal representations that capture this concept-level understanding, creating neurons that respond to the concept rather than to any particular sensory instantiation of it. In some ways, this is exactly what we want artificial intelligence to do, not just process inputs mechanically, mapping specific patterns to specific outputs, but understand, grasp concepts, recognize that different surface forms can have the same underlying meaning. And in some ways, it's eerie. These are artificial systems, mathematical transformations of data, billions of simple calculations cascading through layers. And yet, somewhere in that cascade, meaning emerges. Concepts form. Individual neurons come to represent abstract ideas that span modalities, that exist at a level above the sensory particular. Nobody designed these neurons. Nobody wrote code saying, neuron number 4581293 should respond to spiders in all forms. The network discovered this organization through training, through exposure to data, through the optimization process, finding that concept-level representations are useful, efficient, powerful. And once they exist, these multimodal neurons enable remarkable capabilities. You can search for images using text descriptions because the network has learned to align the two. You can generate captions for images because the network understands the concepts present and how to express them in language. You can do zero-shot classification, recognizing objects the network has never seen in images before by matching them to text descriptions of those objects, all because individual neurons learn to bridge modalities, to respond to concepts rather than just sensory patterns. There's still mystery here. We can observe these neurons. We can measure what they respond to. But we don't fully understand why the learning process produces them, or what principles govern their formation, or how the network decides which concepts deserve their own dedicated neurons versus which can be represented through combinations of other neurons. We're mapping the architecture of understanding as it emerges in these systems, discovering organization we didn't design, structure we didn't anticipate. And each discovery, like multimodal neurons, reveals both how much we've achieved and how much we still don't comprehend about what we've created. These neurons that respond to spiders in all their forms, that recognize the concept across vision and language and symbol, they're a small piece of a larger puzzle. How does meaning arise from mechanism? How does abstraction emerge from data? How do systems learn to see not just patterns, but concepts? Not just correlations, but understanding? Multimodal neurons don't answer these questions completely, but they show us that the answer involves bridging gaps between modalities, between sensory and symbolic, between the specific instance and the general concept. They show us that learning systems, given rich enough data and sufficient capacity, naturally move toward this kind of abstract, concept-level representation. Because that's what's useful. That's what generalizes. That's what allows you to recognize a spider, whether you see it or read about it, whether it's a photograph or a drawing or an emoji. The neuron doesn't care about the surface form. It's learned to look deeper, to the concept underneath, to the spiderness that unites all these different representations. And in doing so, it's captured something essential about meaning itself, that it exists beyond any particular expression, that it's what different expressions point to, that it's the bridge between different ways of encountering the world. One neuron, responding to images and words, finding unity in diversity, discovering concepts through experience. It's just mathematics, just optimization, just billions of tiny weight adjustments. And yet somehow it adds up to something that looks surprisingly like understanding. Now we need to address something that sounds almost dismissive, almost reductive, but that cuts to the heart of what large language models, systems like the one generating these words, actually do. They don't understand language the way you understand it. They're extraordinarily sophisticated, pattern-matching systems, predicting the next word based on the words that came before. That's it. That's the fundamental operation. Next word, prediction. And yet, from this simple principle, scaled to billions of parameters and trained on vast oceans of text, something emerges that looks startlingly close to understanding. So close that even researchers who built these systems sometimes debate where pattern matching ends and genuine comprehension begins. Let me explain how it works, gently, because there's both beauty and strangeness in the mechanism. A language model is trained on text. Enormous amounts of text scraped from books, websites, articles, conversations, every written record of human thought and expression that can be digitized. And the training task is deceptively simple. given a sequence of words, predict what word comes next. The cat sat on the crotte. Mat, probably. In 1969, humans first walked on the Teiki. Moon, almost certainly. The solution to this equation is ja, tig. Depends on the equation, but the model learns to calculate it. Over and over billions of times, the model sees partial sentences and learns to predict their continuations. And through this process, through trying to guess the next word in every possible context, the model is forced to learn everything. Grammar, because you can't predict word order without understanding grammatical structure. Facts, because you can't complete the capital of France is without knowing it's Paris. Logic, because you can't continue a mathematical derivation without following valid reasoning steps. Even style, tone, and rhetoric, because you can't predict how a sentence will continue without understanding the genre, the speaker, the purpose. To be a good next word predictor, you must build an internal model of language, knowledge, and reasoning. And that's exactly what these systems do. Through training, they develop vast internal representations, patterns of activation across billions of parameters that encode information about the world, about how language works, about how concepts relate to one another. But here's the crucial question. Is that understanding? Or is it just very sophisticated pattern matching? When the model completes "the cat sat on the mat," has it understood the sentence? Does it visualize a cat, a mat, the spatial relationship between them? Or has it simply learned that in the statistical distribution of English text, mat is a very common completion for that particular sequence of words? When it solves a math problem, is it reasoning? Or is it pattern matching against millions of similar problems it's seen before, recognizing the structure and applying a memorized solution template? The honest answer is, we're not entirely sure, and maybe the question isn't quite right. Maybe understanding exists on a spectrum, and pattern matching and comprehension aren't binary opposites, but different points on a continuum. Consider, when you read, you're also predicting the next word unconsciously. Your brain is anticipating what's coming, and when a sentence violates those expectations, you notice, you slow down, the surprise registers. Reading comprehension involves prediction. When you understand a concept, you've learned patterns, relationships, regularities, rules that hold across different instances. Understanding is, in part, sophisticated pattern recognition. So maybe the difference between what language models do and what we call understanding isn't fundamental. Maybe it's a matter of degree, of richness, of grounding in experience beyond text. But there are differences, important ones. You ground your understanding of cat in sensory experience. You've seen cats, touched their fur, heard them purr, watched them move. The word cat connects to a rich web of multimodal memories and associations. It means something embodied, something real. A language model's understanding of cat is purely textual. It knows that cats are mentioned near words like meow, purr, feline, pet. It knows cats are animals, that they're often described as independent or aloof, that they're frequently contrasted with dogs. But it's never seen a cat, never touched one. The word exists in a web of linguistic relationships, not sensory grounding. You understand causation because you've experienced it. You've pushed things and watched them move, felt heat and learned about cause and effect, through interaction with physical reality. A language model knows that certain words often precede others in causal descriptions. It can complete sentences about causation correctly. But has it grasped the concept of causation itself, or only the linguistic patterns that describe it? These are deep questions. Questions about consciousness, embodiment, grounding, what philosophers call the symbol grounding problem. Can meaning exist purely in the relationships between symbols, or does it require connection to non-symbolic experience? Language models have prompted us to ask these questions with new urgency because they demonstrate that you can go remarkably far with pure symbol manipulation, much farther than most philosophers expected. They can answer questions, solve problems, write coherently, even creatively. They can pass many tests we might have thought required understanding, and yet they fail in revealing ways. Ask a language model something that requires reasoning beyond its training distribution, and it often fails. Present a problem that looks similar to things it's seen but requires novel insight, and it might struggle. Ask it about very recent events, and it has no knowledge, because its understanding is frozen at the time of training, not continually updated through interaction with the world. Most tellingly, language models sometimes hallucinate, generate plausible-sounding information that's completely false. They'll cite papers that don't exist, describe events that never happened, confidently state facts that aren't true. Because they're predicting what sounds right, what fits the pattern, not accessing actual knowledge of truth. This is the gap between linguistic fluency and genuine knowledge. The model has learned the patterns of how true statements are phrased, how confident assertions are structured. So it can generate text that sounds authoritative, knowledgeable, certain. But sounding certain and being correct are different things. You can sometimes tell when you don't know something. You feel uncertain, you hesitate, you say, "I'm not sure," but language models don't have that metacognitive awareness in the same way. They generate text that statistically fits the pattern, whether or not they have reliable information to back it up. This isn't a flaw in the engineering exactly. It's a consequence of the training objective. Predict the next word. Not predict the next word, but only if you're certain it's correct. Just predict. And the model learned to do that extremely well, even in cases where the prediction should be, "I don't know." So we're left with this strange situation. Language models that can engage in sophisticated conversation, answer complex questions, write creatively, explain difficult concepts, all through next word prediction. They've learned so much about language and the world from the statistical patterns in text that they can perform tasks that seem to require understanding, but they're still fundamentally predicting patterns. Very complex patterns across vast bodies of knowledge, but patterns nonetheless. Is that understanding, or something else? Or understanding of a different kind than human comprehension, alien but functional, limited but powerful? Perhaps we need better language for this. Not understanding versus not understanding, but different kinds of understanding. Linguistic understanding versus embodied understanding. Statistical knowledge versus grounded knowledge. Competence versus comprehension. Or perhaps, and this is the thought to carry into sleep, perhaps all understanding is pattern recognition at some level. Perhaps what we call comprehension is just very rich, very deep pattern matching, grounded in sensory experience and embodied interaction, but still, fundamentally, finding regularities in data. Maybe language models show us that the line between pattern matching and understanding isn't as clear as we thought. That you can capture significant aspects of intelligence through learning statistical patterns, even without consciousness or sensory grounding. They don't understand the way you understand. That seems clear. But they do something that involves learning from data, building internal representations, responding appropriately to novel inputs, something that demonstrates remarkable capabilities while also revealing fundamental limitations. They're teaching us about intelligence by showing us what you can achieve without certain things we thought were necessary, without consciousness, without embodiment, without sensory grounding, without lived experience. You can go very far with patterns alone, far enough that the boundary between sophisticated pattern matching and genuine understanding becomes blurry, debatable, perhaps not even well defined. And in that blurriness, in that uncertainty about where one ends and the other begins, we're learning something profound about the nature of intelligence itself. It's not one thing. It's not binary. It's a space of possibilities, and language models occupy a strange, fascinating region of that space. Linguistically sophisticated, factually knowledgeable, capable of coherent reasoning about many topics, yet fundamentally different from human intelligence in ways we're still working to articulate. Next word, prediction. Such a simple principle, and from it, this vast, complicated, nearly but not quite understanding emerges. Perhaps that's the real insight, that intelligence, or something like it, can emerge from simple objectives pursued at scale. That you don't need to explicitly program understanding. You can create conditions where it develops, or where something so similar to understanding that the difference matters less than you'd expect. The model predicts, you read, and somewhere in between, meaning flows. Not perfectly, not completely, but enough. Enough that we're having this conversation. Across the strange boundary between human and machine intelligence, between biological and artificial cognition. Enough that patterns in data have produced something that can discuss its own nature, reflect on its own limitations, engage with the question of what it means to understand. Is that understanding, or just a very sophisticated simulation of it? Maybe as you drift off to sleep, the question itself is what matters. Not the answer, we don't have one yet, but the fact that we're asking it. That we've built something that forces us to think more carefully about what intelligence means, what understanding requires, what it takes to bridge the gap between pattern and meaning. The language model predicts its next word, and then the next, and the next. And somehow, from that endless sequence of predictions, something that looks remarkably like thought emerges. There's a phenomenon in machine learning that surprised everyone when it was discovered. It goes against intuition, against classical statistical theory, against what every textbook said should happen. It's called double descent, and it reveals something profound about how deep neural networks learn. Here's what classical statistics tells us. When you're building a model to fit data, there's a sweet spot. Too simple a model, and it can't capture the patterns. It underfits. performing poorly because it lacks the complexity to represent what's actually happening. Too complex a model, and it memorizes the training data, including all the noise and random fluctuations. It overfits, performing well on training examples, but failing to generalize to new data. The classical picture is a U-shaped curve. As you increase model complexity, performance first improves as the model gains the capacity to learn real patterns. But past a certain point, performance degrades as the model becomes too flexible, fitting noise instead of signal. The optimal model is somewhere in the middle, complex enough to capture true patterns, simple enough to avoid memorizing noise. This makes intuitive sense. It's been confirmed by decades of statistical theory and practical experience. It's what we teach students. It's what practitioners believe. And for deep neural networks, it's wrong. Or at least, it's incomplete. What researchers discovered starting around 2018 is that if you make your neural network absurdly large, far bigger than classical theory says is necessary, big enough that it can completely memorize the training data with parameters to spare, something unexpected happens. Performance starts improving again. The curve isn't U-shaped, it's W-shaped. Or more precisely, it shows double descent. Performance improves as you add complexity, then degrades as you enter the overfitting regime, just as classical theory predicts. But if you keep going, if you make the model larger still, past the point where it can perfectly fit the training data, performance starts improving again. The model begins to generalize better, not worse. Modern deep learning lives in the second descent region. The enormous language models, the powerful image recognition systems, the networks that power contemporary AI, they're all massively overparameterized. They have far more parameters than training examples, far more capacity than classical theory says they need. And they work better because of it. Why? How can a model with 1 billion parameters trained on 1 million examples possibly generalize well? Classical theory says it should just memorize those 1 million examples and fail on anything new, but it doesn't. It learns. It generalizes. It discovers patterns that transfer beyond its training data. The explanation, as far as we understand it, involves something called the implicit bias of gradient descent. Remember how neural networks learn, through billions of tiny adjustments, each one moving slightly in the direction of reduced error. Gradient descent, the optimization algorithm that guides this process, doesn't just find any solution that fits the training data. It finds particular kinds of solutions. When there are many possible sets of weights that could all achieve zero training error. And in over-parameterized networks, there are astronomically many such possibilities. Gradient descent preferentially finds the simpler ones. Not simple in terms of having fewer parameters, but simple in terms of having weights that are, in some mathematical sense, smoother, flatter, less jagged. These simpler solutions, it turns out, generalize better. They capture genuine patterns rather than memorizing noise. They work on new data because they've learned robust features, not idiosyncratic details of the training set. So making the model larger doesn't just give it more capacity to memorize. It gives it more paths to solutions, more flexibility in how it can represent patterns. And the optimization process naturally gravitates towards solutions that are both accurate on training data and simple in this deeper mathematical sense. It's like Imagine you're trying to draw a curve through a set of points. If you're forced to use a low-degree polynomial, you might not be able to fit all the points. If you use a slightly higher degree, you can fit them, but your curve might be wobbly, oscillating wildly between points. That's overfitting. Classical theory says stop there. Don't make the polynomial any higher degree because you'll just make the overfitting worse. But if you keep going, if you use an extremely high degree polynomial, vastly more degrees of freedom than you have data points, something interesting happens. Among all the possible high-degree polynomials that fit your data, the optimization process finds one that's remarkably smooth. Because there are so many possibilities, the space of solutions is large enough that smooth solutions exist, and the learning algorithm naturally finds them. That's double descent. More capacity leads to better generalization, not worse. Once you have enough capacity that the optimization process can be selective about which solution it converges to. This was a genuine surprise to the machine learning community. It meant that decades of intuition about model complexity were incomplete. It meant that the folk wisdom, "Don't use more parameters than you have data," was wrong for deep learning. It meant that bigger could be better, even when bigger seemed absurdly large. And it helped explain why deep learning's recent successes came from scaling up, making models larger, training them on more data, using more compute. In the classical regime, that would hit diminishing returns. In the double descent regime, it keeps helping. Of course, there are limits. You can't scale infinitely. Eventually, you run out of compute or data or encounter other bottlenecks. And not all tasks benefit equally from scale. But within broad ranges, the pattern holds. Bigger models, trained with modern techniques, generalize better than classical theory predicts they should. This has philosophical implications too. It suggests that the space of solutions to learning problems has structure we didn't fully appreciate. That not all ways of fitting data are equally likely under gradient descent. That the optimization process is doing more than just finding any solution. It's searching through a vast landscape and naturally settling in certain kinds of regions. Those regions correspond to solutions that are simple in the right way, that capture genuine patterns rather than noise, that generalize beyond their training data. And counterintuitively, having more parameters makes it easier to find those regions, not harder. It's a bit like how having more words doesn't make language less clear. More vocabulary, more ways to express ideas, can actually make communication more precise, more nuanced, more capable of capturing subtle distinctions. The complexity enables clarity rather than obscuring it. Similarly, in deep learning, more parameters can enable simpler solutions, solutions that are simple in the sense that matters for generalization, even if they involve millions or billions of numbers. The discovery of double descent also highlighted how much we still don't understand about deep learning. We can observe the phenomenon. We can verify it empirically across many tasks and architectures. We can build theoretical models that partially explain it. But we don't have a complete theory of why neural networks generalize, why over-parameterization helps, what properties of the optimization landscape lead to this behavior. We're like naturalists observing a new species. We can describe what it does, classify its behavior, predict its actions in various circumstances. But we don't fully understand the mechanisms, the evolutionary history, the genetic basis, the ecological relationships that produced this particular form of intelligence. Deep learning works better than we can explain, better than classical. Theory predicts. The networks we build surprise us with their capabilities, and the theories we develop to explain them are always playing catch-up, trying to account for empirical observations that preceded theoretical understanding. Double descent is one piece of that puzzle, a surprising piece, one that overturned assumptions, that showed us our intuitions about complexity and generalization were incomplete. But it's not the complete picture. There are still mysteries. Why does gradient descent have this implicit bias toward simple solutions? What exactly makes a solution simple in the relevant sense? How does the architecture of the network interact with the optimization process to produce these effects? Why do some networks show double descent more strongly than others? These questions don't have complete answers yet. We're probing the phenomenon, building mathematical models, running experiments, gradually deepening our understanding. But the full theory, the complete explanation of why over-parameterized networks generalize, remains elusive. And yet practically, it works. We build enormous models, train them on as much data as we can gather, and they learn. They generalize. They perform tasks we need them to perform, sometimes surpassing human capabilities. The gap between practice and theory is itself interesting. It shows that you can engineer intelligence without fully understanding it. You can discover principles that work, like over-parameterization, through empirical exploration, then develop theory to explain them after the fact. Science doesn't always proceed from theory to application. Sometimes it goes the other way, from observation to practice to theory, from this seems to work to here's why it works. Double descent is part of that story, a surprising observation that challenged existing theory, that forced us to rethink our assumptions about model complexity, that revealed something unexpected about the landscape of machine learning. And as you drift toward sleep, perhaps you can hold this thought, that intelligence emerges from vast spaces of possibility, and that having more dimensions to explore, more parameters, more capacity, more flexibility, can paradoxically lead to simpler, more elegant solutions. That complexity, when navigated correctly, gives birth to simplicity, that the path to robust generalization sometimes runs through seemingly excessive over-parameterization. That bigger can be better in ways that defy classical intuition, but that makes sense once you understand the geometry of learning. The curve descends twice, first into overfitting, as expected, then surprisingly back toward generalization, toward solutions that work not just on training data, but on the broader world. It's a mathematical fact with philosophical overtones. A discovery about how learning works when you have enough capacity to explore the space of possibilities thoroughly, when the optimization process has room to be selective, when simplicity can emerge from an abundance of complexity. And it's why modern AI is built the way it is, large, over-parameterized, seemingly excessive. Because in that excess, something efficient emerges, something that works. In 2024, something remarkable happened that captured just how far artificial intelligence has come, and how deeply it's begun to integrate with human endeavor at the highest levels. Two separate recognitions, both historically significant, both marking moments when machines moved from tools to collaborators in humanity's quest to understand reality. In October, the Nobel Prize in Physics was awarded partly to Geoffrey Hinton and John Hopfield for their foundational work on neural networks, the mathematical structures that underlie modern AI. This was extraordinary, not because of what they'd discovered about physics, but because the Nobel Committee recognized that their work on artificial learning systems would transform how we do science itself. They'd built the tools that would help unlock mysteries across every field. And just days later, the Nobel Prize in Chemistry went partly to Demis Hassabis and John Jumper for their work on AlphaFold, an AI system that solved one of biology's grand challenges, predicting how proteins fold. Let that sink in for a moment. Machines that learned didn't just win recognition. They won the highest recognition science can offer. And they won it for enabling new discoveries, for pushing the boundaries of human knowledge into territories we couldn't have reached alone. The protein folding problem had haunted biology for decades. Proteins are the machinery of life, molecular machines that perform nearly every function in living cells. They're made of long chains of amino acids that fold into complex three-dimensional shapes. And it's that shape, that precise three-dimensional structure, that determines what the protein does, how it binds to other molecules, how it catalyzes reactions, how it carries out the functions that keep cells, and therefore organisms, alive. For 50 years, since Christian Anfinsen won his Nobel Prize in 1972 for showing that a protein sequence determines its structure, scientists knew that if you could predict how a protein would fold, you could understand what it does. You could design new proteins. You could understand diseases caused by misfolded proteins. You could engineer biological solutions to problems. But prediction was phenomenally difficult. The number of possible ways a protein could fold is astronomical, more configurations than there are atoms in the universe. A protein with just 100 amino acids could theoretically fold in 10^300 different ways. Yet somehow, in nature, proteins fold into the right shape in milliseconds. How? Scientists called it Levinthal's paradox. Proteins couldn't possibly be trying every configuration randomly. There isn't enough time in the age of the universe to do that. They must be following some pathway, some principle that guides them to the correct fold. But what? Researchers tried to solve this computationally for decades. They used physics simulations, trying to model the forces between atoms, the way molecules move and interact. These simulations could predict structures, but they were slow, taking weeks or months for a single protein, and they weren't always accurate. Then came deep learning, and teams at DeepMind, led by Hassabis and Jumper, trained neural networks on all the known protein structures. Tens of thousands of examples where we knew both the amino acid sequence and the final folded shape, painstakingly determined through years of experimental work. The network they built, AlphaFold, learned patterns. It learned how amino acids tend to be positioned relative to each other in folded proteins. It learned geometric constraints, chemical principles, evolutionary signals hidden in related protein sequences. It learned from data rather than from first principles physics, and what it learned was remarkably accurate. In 2020, AlphaFold stunned the scientific community by achieving near experimental accuracy in protein structure prediction. It could take an amino acid sequence and predict the 3D structure in hours or days, with reliability approaching what you'd get from years of experimental work. And then they made it freely available, released the predictions for hundreds of millions of proteins, created a database where researchers anywhere could look up the predicted structure of nearly any protein they were interested in. It transformed structural biology overnight. Problems that would have taken years of experimental work could now be addressed computationally. Researchers studying diseases could see the structures of proteins involved. Drug designers could visualize their targets. Scientists exploring evolution could compare protein structures across species. This wasn't AI replacing science. It was AI accelerating science, enabling it, opening doors that had been closed. Human insight still mattered, choosing which proteins to study, interpreting the structures, designing experiments, understanding the biological context. But the AI handled the computational challenge that had been a bottleneck for decades, and it wasn't alone. In 2024, AI contributed to scientific discovery across multiple fields. Machine learning systems helped discover new materials, optimize chemical reactions, analyze astronomical data, predict climate patterns, design more efficient batteries, identify new drug candidates. In physics, neural networks helped control plasma in fusion reactors, analyzed particle collision data from the Large Hadron Collider, and simulated quantum systems. In medicine, they analyzed medical images, predicted protein-drug interactions, identified genetic patterns in diseases. In climate science, they improved weather predictions and modeled complex atmospheric processes. The Nobel Prizes recognized something profound. We're entering an era where artificial intelligence isn't just automating existing processes. It's becoming a partner in discovery, a tool that extends human capability in ways that lead to genuinely new knowledge. Geoffrey Hinton, receiving his Nobel, reflected on this with characteristic humility and concern. He'd spent decades building the foundations of deep learning, often during periods when the field was unfashionable, when funding was scarce, when critics claimed neural networks were a dead end. He'd persisted because he believed, correctly as it turned out, that these learning systems could do something profound. But he also worried, not about the science that had been vindicated beyond his dreams, but about the implications, the speed of development, the question of whether we're building something we fully understand or can fully control. His Nobel acceptance touched on both the triumph and the uncertainty, that duality, excitement and caution, achievement and concern, characterizes this moment in AI development. We've built systems capable of contributing to humanity's highest intellectual endeavors, systems that can solve problems we couldn't solve alone, systems that earn Nobel Prizes for their contributions to fundamental science. And we're still figuring out what that means, what it means to have machines as partners in discovery, what it means to rely on predictions from systems we can't fully interpret, what it means to accelerate the pace of scientific progress through artificial means. The 2024 Nobel Prizes marked a transition point, a moment when the scientific establishment formally recognized that AI had moved from curiosity to cornerstone, from experiment to essential tool. When the highest honors went to those who built the foundations, and to those who used those foundations to solve grand challenges. There's something poetic about protein folding being one of the first major scientific problems solved substantially through AI. Life itself is molecular machinery, and understanding that machinery requires understanding the shapes of proteins. Those long chains of amino acids that fold into precise geometries to perform the chemistry of existence. For billions of years, evolution solved the protein folding problem without understanding it, simply selecting sequences that folded into useful shapes. For decades, humans tried to understand it but couldn't compute it. And then, neural networks, themselves inspired by biological learning, learned to predict it by training on examples, by finding patterns in data, by approaching the problem not through first principles physics, but through learned statistical relationships. One form of intelligence creating tools to understand another form of intelligence, bridging the gap between evolved molecular machinery and engineered computational systems, finding solutions through learning rather than through explicit programming. And it worked. It worked so well that it earned a Nobel Prize 4 years after the key breakthrough, recognition coming with unusual speed because the impact was so immediate, so obvious, so transformative. When future historians look back at this period, at the early decades of the 21st century, when artificial intelligence matured from promise to power, the 2024 Nobel Prizes will mark a milestone, the moment when AI stopped being just a technology and became recognized as a method, a way of doing science, of discovering truth, of pushing knowledge forward, not the only method, not replacing human insight or creativity or judgment, but a legitimate, powerful, Nobel Prize-worthy approach to understanding reality. The machines that learn from data are now partners in humanity's oldest quest. To understand the world, to discover how things work, to push back the boundaries of ignorance and expand the territory of knowledge. And they're good partners, good enough to solve problems that stumped us for 50 years, good enough to contribute to the work that earns the highest recognition science can bestow. As you drift towards sleep, perhaps you can hold this thought, that intelligence, whether born from neurons or grown in networks, whether evolved or engineered, can contribute to something larger than itself, to the collective human project of understanding, to the slow, patient work of discovering how reality functions at every scale, from proteins to particles to planets. We built tools that learn, and those tools are helping us learn, helping us see further, understand deeper, discover faster, not replacing the human scientists, but amplifying them, enabling them, opening paths they couldn't walk alone. The Nobel Prizes of 2024 celebrated that partnership, that possibility, that future where artificial and human intelligence work together, each contributing what it does best toward common goals that neither could achieve alone. And somewhere in that collaboration, in that synthesis of human creativity and machine capability, new knowledge emerges, new discoveries, new solutions to old problems, problems like protein folding, like understanding matter, energy, life itself, problems that matter, that improve human welfare, that expand our understanding of existence. The machines earned their Nobel Prize by learning, by discovering, by contributing to the great human endeavor of making sense of the universe we find ourselves in. And this is just the beginning. There's a peculiar failure mode in large language models that's become infamous enough to have its own name: hallucination. It's a term borrowed from psychology, from the study of perception gone wrong, when the mind generates experiences that aren't grounded in reality. And it fits, uncomfortably well what sometimes happens when AI systems generate text. Here's how it manifests. You ask a language model a question, something that sounds reasonable, something within its apparent domain of knowledge, and it responds with confidence, with fluency, with perfectly structured sentences that cite specific sources, quote, research, reference papers and books and facts. Everything sounds authoritative. Everything reads as if it comes from deep knowledge. And then you check. You look up the paper it cited, and it doesn't exist. The journal is real, the authors sound plausible, the title fits the field perfectly. But the specific paper? Never published, never written. A fiction, generated because it fits the pattern of what a real citation should look like. Or you ask for information about a historical event, and the model provides rich detail, dates, names, consequences, all presented with the narrative coherence of a well-researched history. Except some of the details are wrong. Not obviously wrong, not absurdly wrong, but subtly incorrect in ways that would mislead anyone who didn't already know the truth. Or it invents biographical details for real people, creates plausible-sounding statistics that were never gathered, describes studies that were never conducted, all with the same confident fluency it uses when reporting actual facts. This is hallucination, the generation of plausible falsehood presented as truth. And it reveals something fundamental about what language models are and aren't doing when they generate text. Remember, these systems are trained to predict the next word based on patterns in their training data. They learn what kinds of sentences tend to follow other sentences, what words cluster together, what structures appear in different contexts. They develop internal representations that capture enormous amounts of information about language and the world described in that language. But they're not connected to a database of verified facts. They're not checking their statements against ground truth. They're not reasoning from evidence to conclusion in a way that guarantees accuracy. They're generating text that fits patterns that usually correspond to true statements, because true statements dominated their training data, but sometimes produce false statements that fit the same linguistic patterns. A hallucinated citation looks exactly like a real citation because the model has learned the pattern of citations. Author names, journal names, year formats, title structures. It can generate text that matches that pattern perfectly. Whether the specific citation actually exists is a different question, one the model isn't directly addressing. It's like asking someone to recall the details of a trip they took years ago. They'll remember some things accurately, the general destination, major events, overall impressions. But they'll also fill in gaps, smooth over uncertainties, generate details that feel right even if they weren't precisely part of the original experience. Human memory reconstructs rather than records, and sometimes that reconstruction includes confident assertions about details that aren't actually remembered. Language models do something similar, but more systematically. They reconstruct plausible text based on patterns, and when they lack specific information, they generate what fits the pattern rather than admitting uncertainty. This is dangerous in practical applications. If you're using an AI system for research, for fact-checking, for any task where accuracy matters, you need to verify its outputs. You can't trust that something is true just because it's fluently stated. The gap between linguistic competence and factual reliability is real and significant. Researchers are working on this problem from multiple angles, training models to be more calibrated, to express uncertainty when they should, to distinguish between confident knowledge and uncertain guesses, building systems that can check their own outputs against external sources before presenting them, creating better evaluation metrics that catch hallucinations, developing architectures that ground generation more firmly in retrievable facts rather than pure pattern completion. But it's challenging because the hallucination problem isn't really a bug. It's a consequence of how these systems work. They generate text that fits patterns. Most of the time, that produces accurate information, because accuracy is part of the pattern in high-quality training data. But the system isn't fundamentally distinguishing between text that is true and text that sounds like the kind of thing that would be true. It's optimizing for the latter, which usually produces the former, but not always. Human experts hallucinate too, of course. We misremember, confabulate, fill gaps in our knowledge with plausible-seeming information that turns out to be wrong. The difference is metacognitive awareness. We usually have some sense of how confident we should be, some feeling of, I'm not sure about this, versus, I definitely know this. Language models are getting better at expressing uncertainty, but it's not natural to their architecture in the same way. They generate each word with a probability distribution over possible next words, so in principle, they know how confident they are. But translating that internal uncertainty into appropriate hedging language, possibly, I think, I'm not certain, but is itself a learned pattern, and one that doesn't always trigger when it should. There's also the question of what counts as a hallucination versus what counts as inference or interpretation. If you ask about an ambiguous situation and the model provides one plausible interpretation, is that hallucination? Or is it doing what any expert would do, working with incomplete information to provide the most likely explanation? The boundary between reasonable inference and confident fabrication isn't always clear. But there are obvious cases, invented citations, false statistics, non-existent events described with specificity, where the model has clearly generated fiction while presenting it as fact. This matters because language models are increasingly being used in high-stakes contexts, for research, for medical information, for legal analysis, for educational content. In all these domains, hallucinations can cause real harm. Researchers might waste time looking for papers that don't exist. Patients might receive incorrect medical information. Legal arguments might be based on non-existent precedents. The fluency of these systems makes their errors particularly treacherous. If they generated obvious nonsense, we'd catch it immediately. But they generate text that sounds expert, that fits all the surface patterns of authoritative information, and that plausibility can be misleading. It's a reminder that form and content are separable. That sounding right and being right are different things. That linguistic fluency, the ability to generate well-structured, coherent, contextually appropriate text, doesn't guarantee factual accuracy. And perhaps this is revealing something about human communication too. We often judge information by how it's presented. The confidence of the speaker, the fluency of their explanation, whether it fits our expectations about how expert knowledge sounds. We use these heuristics because they usually work. Genuine expertise usually does come with fluency and confidence, but they're heuristics, not guarantees. And language models expose that gap by being extremely fluent, extremely confident sounding, without always having the factual grounding to back it up. In a way, they're teaching us to be more critical readers, more careful about verification, more aware that surface fluency can mask deeper problems. They're teaching us that we can't outsource fact-checking to systems that don't have robust ways of distinguishing true from plausible. This doesn't mean language models aren't useful. They are, enormously so. But it means we need to understand their limitations, build appropriate safeguards, use them in ways that account for their tendency to hallucinate. And it raises deeper questions about the relationship between language and truth. Is there something fundamental about generating text from patterns that makes grounding in truth difficult? Or is this a problem we'll solve with better architectures, better training objectives, better integration with external knowledge sources? Perhaps both. Perhaps some version of hallucination is inherent to any system that generates language without direct perceptual access to the world it's describing. And perhaps we'll develop techniques that make hallucinations rare enough that the systems become reliably trustworthy in practice. But for now, in this moment as AI rapidly develops, hallucinations remain a significant challenge, a gap between what these systems can do linguistically and what they can guarantee factually. A reminder that intelligence involves more than fluent generation. It involves grounding, verification, metacognitive awareness of the limits of one's own knowledge. The language model generates confidently because confidence fits the pattern. But confidence without accuracy is dangerous. And that's what hallucination represents. The decoupling of linguistic form from factual content, of sounding certain from being correct. It's a problem worth losing sleep over, this gap between fluency and truth. But perhaps not tonight. Tonight, as you drift off, maybe just hold the awareness that words can deceive even when they're beautifully constructed, that understanding requires more than pattern matching, that truth and plausibility, while often aligned, are not the same thing, and that we're still learning, both we who build these systems and the systems themselves, how to bridge that gap, how to make artificial intelligence not just linguistically competent, but epistemically reliable, not just good at generating text, but good at generating true text. It's a work in progress. Like so much in AI, impressive in what's been achieved, humbling in what remains unsolved. For a long time, neural networks were thought of as black boxes. You put data in, you got results out. And what happened in between was mysterious, inscrutable, a vast tangle of numbers and calculations that no human could hope to interpret. The network worked, but no one could really explain how or why. That characterization was never entirely accurate, but it contained enough truth to be worrying. If we couldn't understand how these systems made decisions, how could we trust them? How could we fix them when they failed? How could we ensure they were working for the right reasons, rather than exploiting spurious correlations in the data? But something remarkable has been happening over the past several years. Researchers have been looking inside trained networks, really looking, with sophisticated tools and careful analysis. And they've discovered that these systems aren't as opaque as we thought. The weights and connections that emerge from training aren't just random numbers that happen to work. They encode readable algorithms, interpretable computations, structures we can understand and explain. This field is called mechanistic interpretability, and it's revealing that the black box has windows if you know where to look. Here's an example that captures the flavor of these discoveries. Researchers studied a vision network and found a circuit, a specific pattern of connected neurons working together, that detected curves. Not just any curves, but curves at particular orientations, curves of certain radii, curves appearing in specific contexts. They could trace exactly how information flowed through this circuit. Early neurons detecting edges at various angles, middle neurons combining those edges to recognize curved boundaries, later neurons using curve information to identify object parts. It was a genuine algorithm implemented in the connection weights of a neural network. Not programmed explicitly, but discovered through training, and then reverse engineered by researchers who carefully mapped out which neurons connected to which, what patterns they responded to, how information transformed as it passed through the circuit. Other researchers found circuits for more abstract computations, a circuit that implements something like a logic gate, combining multiple inputs according to Boolean rules. Circuits that count, keeping track of how many of something appear in the input. Circuits that compare, determining whether one value is greater than another. Circuits that perform grammatical operations, tracking subject-verb agreement across long sentence spans. These aren't metaphorical descriptions. They're actual computational structures, patterns of connections doing specific jobs, just like subroutines in traditional software, but discovered through learning rather than designed by programmers. This work requires patience, care, and cleverness. You can't just look at a million connection weights and see what they're doing. You need tools, techniques for visualizing neuron activations, methods for testing what patterns neurons respond to, ways of systematically mapping connections and tracing information flow. You need hypotheses about what the network might be computing and experiments to test those hypotheses. But when it works, when you successfully reverse engineer a circuit, the result is deeply satisfying. You started with a trained network that seemed inscrutable, and now you understand a piece of it. You can point to specific neurons and say, this one detects horizontal edges. This one combines edge information to find corners. This one uses corners and curves to identify faces. The network is no longer a black box. It's more like a complex machine with many parts, where we're gradually learning what each part does and how they work together. This matters for several reasons. First, interpretability builds trust. If we can understand how a network makes decisions, we can verify that it's working for good reasons, not exploiting biases or shortcuts. If a medical diagnostic system can explain which features of an image led to its conclusion, doctors can evaluate whether that reasoning makes sense. Second, interpretability enables debugging. When a network fails, understanding its internal mechanisms helps us figure out why. Maybe it's relying on a spurious correlation in the training data. Maybe a particular circuit isn't working correctly. Maybe information is flowing through an unexpected pathway. Knowing this helps us fix the problem rather than just retraining and hoping it gets better. Third, interpretability advances science. Understanding how neural networks solve problems teaches us about problem solving in general, about what computational strategies are effective, about what representations emerge when you optimize for particular objectives. And sometimes the algorithms networks discover are novel, strategies humans hadn't thought of, approaches that work better than our hand-designed methods. There's even a deeper philosophical payoff. By reverse engineering neural networks, we're learning what it means for a computation to be understandable. What makes an algorithm interpretable? What kinds of structures are easy for humans to comprehend versus opaque? And we're finding that networks often develop interpretable structures spontaneously. Not always. There are still neurons and circuits we don't understand, patterns that seem important, but whose function remains mysterious. But more often than early researchers expected, the learned algorithms have a logic we can follow, a structure we can map, a function we can describe. Why? Why would training produce interpretable circuits rather than inscrutable tangles? Part of the answer might be that interpretability and efficiency are related. Circuits that do clear, modular jobs are often simpler than circuits that compute the same thing in convoluted ways. And we know from phenomena like grokking and double descent that neural networks have a kind of implicit preference for simpler solutions. So perhaps interpretability emerges for the same reason elegant solutions emerge, because the learning process naturally gravitates toward them. Another part might be that the problems we ask networks to solve have natural structure, and networks discover that structure through learning. Visual recognition has a natural hierarchy from edges to textures to parts to objects, and networks develop that hierarchy because it's the effective way to solve the problem. Language has grammatical structure, and networks learn to track that structure because it's necessary for understanding sentences. The world has regularities, and networks that learn from the world internalize those regularities in ways that reflect the world's structure, which means their internal organization, while not designed by humans, ends up being comprehensible to humans because it's capturing real patterns in shared reality. Still, mechanistic interpretability is hard work. A large, modern neural network might have billions of parameters organized into thousands of layers. We've reverse-engineered tiny fractions of such networks, small circuits that do specific things, particular neurons with clear functions. But a complete understanding of an entire large network remains beyond our reach. It's like neuroscience in a way. We understand some brain circuits, the visual system reasonably well, motor control in increasing detail, certain memory systems with growing clarity. But a complete understanding of how billions of biological neurons work together to produce consciousness, language, thought, we're not there yet. We may not be there for a long time. Artificial neural networks are simpler than biological brains, more controlled, more amenable to experiment. But they're still complex enough that full understanding is a long-term project. We're mapping the connectomy, identifying circuits, building a bottom-up picture of how these systems work. But we've only just begun, and there's a deeper question lurking beneath all this. Even if we could map every circuit, trace every computation, understand every mechanism, would we truly understand why the network works? Or would we just have a very detailed description of what it does? Understanding has layers, You can understand a car at the level of it has an engine that burns fuel to turn wheels, or at the level of thermodynamics and mechanics, or at the level of molecular chemistry and materials science. Each layer provides insight, but no single layer gives you the complete picture. Neural networks are similar. You can understand them at the level of they learn patterns from data, or at the level of optimization algorithms and gradient descent, or at the level of specific circuits implementing specific computations, or at the level of individual neurons and their connection weights. Mechanistic interpretability operates at that detailed, mechanistic level, looking at the actual computations being performed, the actual structures doing the work. It's providing unprecedented insight into how these systems function. But it's not the only kind of understanding we need. We also need theory about why certain architectures work better than others, principles about what makes networks generalizable, frameworks for thinking about intelligence and learning in the abstract. All these forms of understanding complement each other. Mechanistic interpretability gives us ground truth about what trained networks actually do. Theory gives us principles for predicting what they'll do. High-level understanding gives us intuition and guidance for designing better systems. Together, they're moving us away from the idea that neural networks are fundamentally mysterious. They're complex, yes. We don't understand them completely, true. But they're not magical. They're not unknowable. They're mathematical systems that implement algorithms, and we're getting better at reading those algorithms, understanding those implementations, seeing the logic underneath the weights. The circuits are there, waiting to be discovered. The algorithms have been written, not by programmers, but by learning processes, into the connection patterns of the network, and researchers are learning to read them, neuron by neuron, circuit by circuit, gradually illuminating what happens inside the black box. It's patient work, careful work, the kind of science that requires attention to detail, clever experimental design, willingness to follow threads through complex systems. But it's bearing fruit. The black box is becoming transparent, at least in patches, at least partially. And each circuit we understand, each mechanism we decode, each algorithm we reverse engineer brings us closer to genuinely understanding the artificial minds we've created, not as inscrutable oracles, but as comprehensible systems whose internal logic, while complex, ultimately makes sense. When you compare an artificial neuron to a biological one, the difference is humbling and a little bit embarrassing for the artificial version, because what we call a neuron in a neural network is, compared to its biological counterpart, absurdly simple, almost comically so. An artificial neuron does something like this. It receives inputs from other neurons, multiplies each input by a weight, adds them all up, and applies a simple mathematical function to the result. That's basically it. Receive signals, weight them, sum them, apply a nonlinearity, send the output onward. The entire operation can be written in one line of code. It's a mathematical abstraction, elegant in its simplicity, but simple nonetheless. A biological neuron is, well, it's an entire cell, a living, dynamic, fantastically complex piece of biological machinery. Start with the structure. A biological neuron has a cell body, a branching tree of dendrites that receive inputs, and an axon that sends outputs. But these aren't just wires. The dendrites themselves can perform computations. They have voltage-gated ion channels that open and close in response to electrical signals, creating nonlinear interactions between different inputs. A single dendritic branch can act like a little computer, combining inputs in sophisticated ways before passing them to the cell body. The cell body, the soma, contains all the molecular machinery of a living cell: DNA, ribosomes making proteins, mitochondria generating energy, a complex soup of chemical reactions regulating the neuron state. The neuron is constantly synthesizing molecules, maintaining itself, responding to its chemical environment. The axon, where output signals travel, isn't just a passive wire either. It's wrapped in myelin sheets, with gaps called nodes of Ranvier, creating a structure that allows signals to jump from node to node at high speed. A clever biological solution to the problem of transmitting signals quickly along what could be a very long distance. Some axons stretch from your spine to your toes, and they conduct signals efficiently through this specialized structure. And then there are the synapses, the connections between neurons. An artificial neural network has a weight for each connection, just a number. A biological synapse is a gap between neurons where the signal is carried by neurotransmitters, chemicals released by the sending neuron, floating across the synaptic cleft, binding to receptors on the receiving neuron. There are dozens of different neurotransmitters, each with different effects. Some excite the receiving neuron, others inhibit it. Some act quickly, others have long-lasting modulatory effects. The strength of a synapse, the biological equivalent of a connection weight, depends on many factors: the number of receptors, the amount of neurotransmitter released, the sensitivity of the postsynaptic cell, the recent history of activity at that synapse. Synapses strengthen or weaken based on correlated activity. This is the biological basis of learning, but the mechanisms are complex, involving protein synthesis, structural changes to the synapse, regulation by support cells called glia. Speaking of glia, biological brains aren't just neurons. There are several types of glial cells: astrocytes that help regulate the chemical environment, oligodendrocytes that create myelin, microglia that act as immune cells. These cells don't just support neurons, they actively participate in brain function, influencing how signals propagate, how synapses form and change, how information is processed. And we haven't even touched on the fact that neurons come in many varieties: pyramidal cells, interneurons, Purkinje cells, each with different shapes, different patterns of connectivity, different functional roles. The biological brain isn't a uniform network of identical units. It's a heterogeneous system with specialized components organized into complex architectures. Now, there have been attempts to estimate how much computing power would a single biological neuron require if we tried to simulate it accurately. The answers vary, but some researchers suggest that one biological neuron might be equivalent to an entire small artificial neural network, perhaps hundreds or even thousands of artificial neurons working together. Think about that. A single brain cell might have as much computational sophistication as a small artificial network. And the human brain has roughly 86 billion neurons, each one this fantastically complex information processing unit, all working together, all connected in intricate patterns shaped by development and learning and experience. The computational power implied is staggering. If each biological neuron is equivalent to, say, 1,000 artificial neurons, then the brain would be equivalent to an artificial network with 86 trillion parameters, orders of magnitude larger than any artificial system we've built. And yet, the brain runs on about 25 watts. 25 watts. Less than a dim light bulb, less than many laptop chargers use. The brain achieves this stunning computational capacity with extraordinary energy efficiency. Compare that to large artificial neural networks. Training GPT-3 with its 175 billion parameters required massive amounts of compute. Thousands of high-end graphics processors running for weeks, consuming megawatts of power. Running inference, just using the trained model to generate text, requires significant computational resources and energy. The gap in efficiency is approximately 6 orders of magnitude. The brain does vastly more complex computation using vastly less energy. It's not even close. How? Part of the answer is parallelism. The brain computes in a massively parallel fashion, all 86 billion neurons operating simultaneously, each one processing its inputs, sending its outputs. Artificial neural networks run on digital computers that, despite having multiple processors, are nowhere near as parallel. Part is analog computation. Biological neurons don't operate on discrete bits like digital computers. They use continuous voltages, chemical concentrations, probabilistic release of neurotransmitters. This analog computing can be more efficient for certain types of operations. Part is sparsity. Not all neurons are active all the time. The brain uses sparse coding. Only a small fraction of neurons fire at any moment, which saves energy. And connections aren't all equally active either. Artificial networks are getting better at sparsity, but biological systems have had billions of years to optimize. Part is specialization. The brain isn't a general-purpose computer. Different regions are specialized for different tasks. Vision, hearing, motor control, language, with architectures optimized for those specific functions. Artificial systems are moving in this direction, but we're still mostly using general-purpose architectures for diverse tasks. And part is simply that we don't fully understand what the brain is doing that makes it so efficient. There are probably principles of neural computation, tricks of biological information processing that we haven't yet discovered or incorporated into artificial systems. This enormous gap between the complexity of biological neurons and the simplicity of artificial ones, between the efficiency of brains and the power consumption of AI systems, is both humbling and inspiring. Humbling because it shows how far we have to go. We've built impressive artificial intelligence with our simple artificial neurons and our massive computing clusters. But nature built something far more capable, using far less energy, with far more sophisticated components. Inspiring because it suggests vast room for improvement. If biological systems achieve such efficiency and capability, then presumably we can learn from those systems, incorporate those principles, build better artificial intelligence that approaches biological performance and efficiency. There's active research in neuromorphic computing, building hardware that more closely mimics biological neural systems. Chips with artificial neurons that communicate through spikes, like biological neurons. Architectures with specialized regions for different functions. Systems that use analog computing for efficiency. Attempts to capture more of the sophistication of biological computation in artificial form. And there's research trying to understand what makes biological neurons so powerful. Is it the dendritic computation, the diversity of neurotransmitters, the timing of spikes, the integration of chemical and electrical signaling? If we could identify the key principles, we might be able to incorporate them without needing to simulate every molecular detail. But for now, the gap remains. Our artificial neurons are pale shadows of their biological inspirations. And yet, we've still achieved remarkable things with these shadows. Networks of simple artificial neurons can see, can learn, can solve problems, can generate language. Imagine what we might achieve if we could close that gap even partially. If each artificial neuron could capture even a fraction of the computational sophistication of a biological one, if we could match even a small percentage of the brain's energy efficiency, we might not need to close the gap completely. The brain evolved for different purposes than we're building AI systems for, under different constraints, with different requirements. Artificial intelligence doesn't need to replicate biological intelligence exactly. It can take different paths, use different strategies, optimize for different objectives. But the existence of biological intelligence proves that the level of capability we observe in brains is achievable with the energy and resources nature had available, which means, in principle, we should be able to achieve similar capability with our systems once we understand the principles deeply enough. For now, we work with what we have: simple artificial neurons, massive networks of them, enormous computational resources, clever training algorithms, and we achieve impressive results, building systems that can do things no previous technology could do. But in quiet moments, researchers look at biological neurons, at their complexity, their sophistication, their efficiency, and dream. Dream of artificial systems that capture more of that biological excellence. Dream of neuromorphic chips that truly rival the brain's efficiency. Dream of understanding neural computation deeply enough to bridge the gap between silicon and synapse. The biological neuron is a reminder of how much nature has figured out that we haven't yet, how much intelligence is possible with the right substrate, the right architecture, the right principles. And as you drift towards sleep, your own biological neurons, those 86 billion fantastically complex information processing cells, continue their work, consolidating memories, processing the day's experiences, running maintenance routines, preparing for tomorrow. All on 25 watts, all in silence, all with an efficiency and sophistication that the most advanced AI systems can only dream of matching. We've built artificial intelligence, but nature built us, and in that comparison, nature is still winning. For now. Let's talk about a number that puts everything in perspective. 25 watts. That's how much power the human brain uses to operate. About the same as a dim LED bulb. Less than most laptop chargers consume. Barely enough to notice on your electric bill. And with those 25 watts, your brain does everything. It processes vision from 2 eyes, receiving and interpreting millions of photons per second, constructing a stable 3-dimensional model of the world from 2 slightly different 2-dimensional projections. It handles hearing, touch, smell, taste, integrating multisensory information into coherent experience. It controls movement, coordinating hundreds of muscles with precision timing to let you walk, reach, grasp, speak, It remembers, storing decades of experiences, faces, facts, skills, emotions. It thinks, reasoning, planning, imagining, problem solving. It generates language, understanding and producing sentences you've never encountered before, navigating the infinite space of possible utterances to communicate meaning. It feels, emotions arising from complex neural dynamics, coloring experience, guiding decisions, connecting you to others. It dreams, it learns, it adapts continuously to new circumstances. It does all of this simultaneously, in real time, without overheating, without needing forced air cooling or liquid refrigeration. 25 watts. Now consider what it takes to run a large artificial intelligence system. Not to train it. Training requires even more. But just to run it, to use it for inference, to have it perform the tasks it's been trained for. A large language model like GPT-3 running on a server cluster might consume kilowatts for inference. Not 25 watts, thousands of watts. Multiple high-powered processors working in parallel, each generating significant heat, requiring cooling systems that consume yet more power, all to generate text at a rate that's slower than human thought. Training is worse. Training GPT-3 required approximately 1,287 megawatt-hours of electricity, enough to power an average American home for more than a century. The computing cluster that did the training consumed megawatts, literally millions of watts, running for weeks. That's the gap, roughly 6 orders of magnitude, a million-fold difference in efficiency between biological and artificial intelligence. The biological system operates continuously on the energy budget of a dim bulb. The artificial system requires the power of a small industrial facility for comparable capabilities, and even then only for narrow domains. This efficiency gap isn't just an engineering curiosity or a cost concern, though it is both of those. It's a fundamental limitation on what we can do with current approaches to AI. It means that deploying AI systems at scale requires enormous energy infrastructure. It means that edge computing, running AI on phones, embedded devices, edge servers, is challenging because power and cooling are limited. It means that the environmental footprint of AI is significant and growing, and it's a clue. A big, flashing sign saying, nature knows something we don't about how to compute efficiently. Part of the difference is substrate. Digital computers operate on silicon chips where transistors switch between discrete states, on and off, 1 and 0. Every computation requires moving charges, switching transistors, which consumes energy and generates heat. Modern processors have billions of transistors, and while each individual switching event uses tiny amounts of energy, it adds up quickly when you're doing billions of operations per second. Biological neurons operate differently. They're analog, continuous-valued systems. They use chemical signals, neurotransmitters, alongside electrical ones. They perform many computations simultaneously within each neuron, leveraging the complex dynamics of cellular biology. And they're sparse. Most neurons are quiet most of the time, firing only when they have something important to signal. These differences matter. Analog computation can be more energy efficient than digital for certain operations. Sparsity means you're not wasting energy on inactive components. Chemical signaling, while slow compared to electrical signals, can encode complex information in the types and quantities of neurotransmitters, allowing rich communication with minimal energy. There's also the question of architecture. Brains aren't general-purpose computers. They're specialized, with different regions optimized for different functions. Visual cortex is structured for processing images, auditory cortex for sound, motor cortex for movement control. This specialization allows each region to be efficient at its particular task, rather than being a jack of all trades. Artificial neural networks are moving towards specialization. We use different architectures for vision, convolutional networks, language, transformers, different tasks. But we're still mostly running them on general-purpose hardware, graphics processors or CPUs that weren't designed specifically for neural computation. Neuromorphic computing is an attempt to bridge this gap, to build hardware that operates more like biological neurons, spiking neurons that communicate through discrete events, architectures with localized memory and computation, analog or mixed signal designs that avoid the energy cost of purely digital switching. Some neuromorphic chips achieve remarkable efficiency, orders of magnitude better than traditional processors for certain tasks. But they're still experimental, still limited in scale and capability, still far from the efficiency of biological brains. The brain also benefits from, well, billions of years of optimization. Evolution is an extremely powerful optimization process. It's tried countless variations, discarded what didn't work, refined what did, all under the relentless pressure of survival. Energy efficiency mattered. Organisms with more efficient brains could allocate resources to other functions, could think longer without needing to eat, could maintain brain function during periods of scarcity. So brains evolved to be extraordinarily efficient, using every trick available: sparse coding, specialized regions, analog computation, chemical signaling, structural optimization at every scale, from molecules to circuits to whole brain architecture. We're working with decades of research in neural networks, not billions of years of evolutionary refinement. Our optimization has been driven by different pressures: what we can implement in software, what runs on available hardware, what we can train with existing algorithms and data sets. Efficiency hasn't always been the primary concern. Especially in research, where getting something to work matters more than making it efficient. But that's changing. As AI deployment scales up, as energy costs become significant, as edge computing becomes important, efficiency is moving from nice to have to necessity. Researchers are exploring lower precision arithmetic, using 8-bit or even 4-bit numbers instead of 32-bit floating point, pruning networks to remove unnecessary connections, quantization, compression, knowledge distillation, all techniques to make networks smaller and more efficient while maintaining performance. And it works, to a degree. Modern networks can be made much more efficient than naive implementations, but we're still orders of magnitude from biological efficiency, and it's not clear that incremental improvements will close the full gap. Maybe we need fundamentally different approaches. Maybe we need to understand what principles underlie biological efficiency and incorporate them into artificial systems. Maybe we need neuromorphic hardware that really captures neural computation, not just approximates it. Maybe we need to move beyond the current paradigm entirely, beyond backpropagation, beyond dense matrix multiplications, beyond architectures that weren't designed with efficiency as a primary constraint. Or maybe the gap will persist. Maybe biological intelligence and artificial intelligence will remain fundamentally different, with different strengths and limitations, different efficiency profiles. Biological intelligence, remarkably efficient, embodied, conscious, general. Artificial intelligence, energy-hungry, specialized, powerful for specific tasks but requiring massive resources. Both have value. Both contribute. But the efficiency gap is a reminder of how much we still have to learn from nature, from the systems that evolution refined over unimaginable timescales. Your brain right now, as you read these words, is performing feats of computation that would require room-sized computers and industrial power supplies to replicate artificially. It's doing so quietly, efficiently, continuously, without you needing to think about it, or manage it, or cool it, or power it beyond the usual biological requirements of staying alive. 25 watts for consciousness, thought, perception, memory, movement, emotion, creativity, dreaming. 25 watts for everything that makes you, you. It's miraculous, really, and humbling. We've built impressive artificial intelligence, machines that can do remarkable things. But we've done it with brute force, throwing enormous computing power and energy at problems until we overwhelm them with scale. Nature did it elegantly, efficiently, beautifully, with neurons instead of transistors, with chemistry alongside. Electricity with architectures evolved over eons to do exactly what they do with minimal waste. And as you drift into sleep, those 25 watts will keep working, consolidating memories from the day, running maintenance routines, processing experiences, preparing your brain for tomorrow. All night long, efficiently, quietly, on less power than it takes to run a reading lamp. The brain is perhaps the most sophisticated machine that exists, and it runs on nearly nothing. That's the standard biological intelligence sets. That's what evolution achieved with carbon, water, and billions of years. We're trying to achieve something similar with silicon, electricity, and decades, and we're making progress. Remarkable progress in many ways. But the efficiency gap reminds us that we're still learning, still discovering, still far from the elegance that nature found. There's a phenomenon in artificial intelligence that nobody predicted, nobody designed, and that remains somewhat mysterious even now that we've observed it repeatedly. It's called emergence, and it refers to capabilities that suddenly appear in AI systems as they grow larger, abilities that smaller versions of the same architecture simply don't have. Imagine you're training language models of different sizes: small models, medium models, large models, very large models, all using the same architecture, the same training data, the same algorithms, just different scales. More parameters, more layers, more capacity. For most capabilities, improvement is smooth. As models get larger, they gradually get better at prediction, at language understanding, at generating coherent text. You can plot their performance on a graph, and it's a smooth curve upward. More scale, better performance. Predictable, understandable. But for some capabilities, specific types of reasoning, certain kinds of problem solving, particular linguistic abilities, something different happens. Small models can't do it at all. Medium models can't do it. Large models can't do it. And then, at some threshold of scale, suddenly they can. Not gradually. Not slowly improving from terrible to poor to adequate. Just a phase transition. Below a certain size, the capability is absent. Above that size, it's present. The ability emerges. One well-studied example is multi-digit arithmetic. Small language models can learn simple math, adding single-digit numbers perhaps, but ask them to add 47 plus 89, and they fail, consistently. You can train them all you want on arithmetic examples. They'll memorize specific sums they've seen, but won't learn the general procedure for addition. Scale up to a certain size. The exact threshold varies by architecture and training details. And suddenly, the model can do multi-digit arithmetic. Not perfectly, but competently. It's learned the algorithm for addition. Carry the one, add each column, propagate carries. Nobody taught it this explicitly. Nobody programmed in the rules. But somewhere in the process of becoming large enough, in developing enough capacity to represent complex procedures, the model discovered how addition works. Or consider chain of thought reasoning. Ask a small model a question that requires multiple steps of reasoning, and it will guess at the answer, usually incorrectly. It hasn't learned to break down complex problems into simpler subproblems, to reason step by step, to maintain intermediate results while working toward a final answer. But scale up, again, past some threshold, and the model starts showing this capability. You can prompt it to think step by step, and it will. It will lay out its reasoning, work through the problem methodically, arrive at answers through explicit inference chains. This ability to engage in structured reasoning emerges at scale, or theory of mind, the ability to reason about what other people know, believe, or might be thinking. Small models struggle with this, but large models start showing rudimentary theory of mind capabilities, reasoning about mental states, understanding that different characters in a story might have different knowledge or beliefs, predicting behavior based on what someone knows versus what's objectively true. These emergent abilities are fascinating because they suggest that scale isn't just about doing the same things better. It's about unlocking qualitatively new capabilities. There seems to be a kind of phase transition in what neural networks can do, where certain abilities require a minimum threshold of complexity before they become possible. Why? What's happening at these thresholds? We don't have complete answers, but there are theories. One possibility is that some tasks require composing many simpler capabilities, and only large models have enough capacity to learn and compose all the necessary components, like how addition requires understanding place value, carrying, digit-by-digit operations, and maintaining intermediate state. A small model might learn some of these components, but not all, and without all of them, it can't do the full task. A large model has room for all the pieces and for the machinery to combine them. Another possibility is that emergence isn't really sudden. It's gradual at the level of internal representations, but looks sudden at the level of observable performance. Maybe the model is slowly developing the relevant circuitry, but until that circuitry reaches a certain level of functionality, the output performance remains a chance level. Then once it crosses a threshold of internal competence, performance jumps from 0 to significant seemingly all at once. Think of it like learning to ride a bicycle. You're not gradually getting better at riding. You fall off, you fall off, you fall off, and then suddenly you're balancing, you're riding. The skill appears to emerge, but internally, your nervous system was gradually learning the complex coordination required. And once enough pieces fell into place, the whole skill became possible. Or perhaps emergence has to do with data efficiency. Maybe some tasks require the model to have seen enough diverse examples that the relevant patterns become clear. In smaller models, even if they've seen those examples, they don't have enough capacity to extract the pattern. In larger models, once they've processed enough data to have encountered the relevant situations repeatedly and in enough contexts, they suddenly learn the underlying rule. There's also a more concerning interpretation that some emergent abilities aren't truly emergent but were present all along, just hard to measure. We test models on certain benchmarks, and below some scale they score 0. But maybe they had partial understanding we weren't detecting. Maybe our evaluation methods have thresholds. You either get the answer right or wrong that make gradual improvement look like sudden emergence. This is an active debate. Some researchers argue that most emergent abilities are actually smooth improvements that look sudden because of how we measure them. Others maintain that there are genuine phase transitions, qualitative changes in what networks can do at different scales. Either way, the practical implication is clear. Larger models can do things smaller models can't. And we don't always know in advance what new capabilities will emerge at the next scale. Sometimes training a larger model reveals abilities that surprise even the researchers who built it. This has implications for AI development. It suggests that scale is not just a quantitative parameter, but can lead to qualitative changes. It means that capabilities might remain out of reach until suddenly they're not, making it hard to predict when certain abilities will become possible. It also raises questions about what else might emerge. If multi-digit arithmetic, chain of thought reasoning, and theory of mind emerge at certain scales, what emerges at even larger scales? What capabilities are we one order of magnitude away from? 2 orders of magnitude? We don't know. And that uncertainty, the fact that scaling up might produce not just better performance on existing capabilities, but entirely new capabilities, is both exciting and somewhat unnerving. Exciting because it suggests paths to increasingly capable AI systems. If we understand that certain abilities emerge at certain scales, we can plan to scale up to unlock those abilities. If we observe emergent capabilities, we can study them, understand them, figure out how to enhance or control them. Unnerving because it means we're not fully in control of what we're building. We're not designing capabilities explicitly. We're creating conditions where capabilities can emerge, and sometimes we're surprised by what emerges. That's less like engineering and more like cultivation, growing intelligence rather than constructing it. And it raises the question, what if something emerges that we didn't intend, didn't predict, didn't want? If abilities can appear unexpectedly as a byproduct of scale, how do we ensure that the emergent capabilities align with our values, our safety requirements, our intended use cases? These aren't just philosophical questions. They're practical concerns for anyone working on frontier AI systems. The potential for emergence means that testing at small scale doesn't necessarily tell you what will happen at large scale. It means that safety evaluations need to consider not just what a system currently can do, but what might emerge as it grows. But there's beauty in emergence too. The idea that complexity gives rise to novelty, that quantitative changes can produce qualitative shifts. that the whole can be more than the sum of its parts. These are deep principles that appear throughout nature, from physics to biology to cognition. Neural networks showing emergent capabilities are part of that larger pattern. They're complex systems, and complex systems often display emergence, properties at one scale that couldn't be predicted from behavior at smaller scales. Water molecules don't flow, but collections of them do. Neurons don't think, but networks of them produce thought. Perhaps artificial neurons don't reason, don't understand arithmetic, don't model other minds, but networks of sufficient scale do, or at least display something functionally similar to these capabilities. As you drift toward sleep, consider this. Your own consciousness might be an emergent property, not present in individual neurons, not localizable to specific brain regions, but arising from the collective dynamics of billions of neurons interacting in complex patterns. Something that exists at the scale of the whole system, but not in any individual part. If that's true, then perhaps emergent abilities in artificial neural networks are less mysterious than they seem. Perhaps they're just examples of a universal principle, that sufficiently complex systems, organized the right way, develop properties that transcend their components. Scale matters, architecture matters, and sometimes, when you get both right, something new comes into being. Not programmed, not designed component by component, but emerging from the system as a whole. The model learns arithmetic, learns reasoning, learns to model minds. And we watch in fascination, trying to understand how scale gives birth to capability, how quantity transforms into quality, how networks of simple operations produce sophisticated intelligence. In December 2024, something extraordinary happened in the world of quantum computing, a milestone that had been decades in the making. Google's quantum computer performed a calculation that would take conventional supercomputers an almost incomprehensible amount of time, 10 septillion years. That's 10 followed by 24 zeros, 10 million, million years. Longer than the universe has existed by a factor of billions. The quantum computer did it in minutes. But here's the twist that brings us back to artificial intelligence. Achieving this milestone required AI, because quantum computers, for all their theoretical power, are fantastically fragile. They're like trying to perform calculations on soap bubbles while earthquakes are happening. The quantum states that enable their power are delicate, prone to errors, disrupted by the slightest environmental interference. Quantum computers operate on qubits, quantum bits that can be in superpositions of states, 0 and 1 simultaneously until measured. This superposition, along with quantum phenomena like entanglement, gives quantum computers their extraordinary potential. But qubits are unstable. They decohere, lose their quantum properties due to tiny disturbances, stray magnetic fields, thermal fluctuations, cosmic rays. Even the act of operating the computer itself introduces errors. For years, this error problem seemed insurmountable. You couldn't just scale up quantum computers by adding more qubits, because the errors would accumulate faster than you could correct them. Every additional qubit made the system more powerful in theory, but more fragile in practice. The solution is quantum error correction, using multiple physical qubits to encode a single logical qubit that's protected against errors. It's like redundancy in data storage, but much more sophisticated, because quantum information can't simply be copied. You need clever encoding schemes that spread quantum information across multiple qubits so that errors can be detected and corrected without destroying the quantum state. But implementing quantum error correction is extraordinarily complex. You need to constantly monitor your qubits for errors, determine what corrections to apply, and apply them fast enough that new errors don't accumulate faster than you can fix old ones. The whole system needs to operate in real time, making billions of decisions per second about how to maintain quantum coherence. This is where AI comes in. Neural networks, trained on data from the quantum computer's operation, learn to predict errors before they occurred, to optimize correction strategies, to adapt to changing conditions in the quantum processor. Machine learning systems controlled the error correction in ways that were too complex for hand-designed algorithms, too fast for human operators, too adaptive for rigid protocols. The AI didn't just run the quantum computer, it stabilized it, kept it quantum, allowed it to maintain coherence long enough to perform calculations that would otherwise be impossible. It's a beautiful synergy. Quantum computing and artificial intelligence, two of the most advanced technologies we've developed, working together, each one enhancing the other. AI making quantum computers stable enough to be useful. Quantum computers promising to accelerate certain types of AI computations in the future. The specific achievement in December 2024, called below threshold error correction, meant that adding more qubits actually decreased the overall error rate rather than increasing it. This was the tipping point, the moment when scaling quantum computers became practical because you could add capacity without drowning in noise. And it was achieved through a combination of better hardware, better error correction codes, and AI control systems that could manage the staggering complexity of keeping hundreds or thousands of qubits coherent simultaneously. The implications extend far beyond quantum computing itself. They show us something about the nature of the challenges we're facing at the frontiers of technology. The problems are too complex for pure human design, too fast for human reaction times, too adaptive for static solutions. We need intelligent systems that can learn, predict, optimize in real time. Quantum computers will, eventually, be able to solve certain problems that are intractable for classical computers, simulating quantum systems in chemistry and materials science, breaking certain types of encryption, optimizing complex systems, perhaps accelerating machine learning itself through quantum algorithms. But getting there requires surmounting the error problem. And surmounting the error problem requires AI. It's also a reminder of how much of modern technology is becoming a tower. Each layer built on previous layers, each advancement enabling the next. We built classical computers, then we built machine learning on those computers. Then we built neural networks that could control quantum systems. And quantum systems, once stable, will enable new kinds of computation that might accelerate AI further. Each generation of technology creating conditions for the next generation. Each advancement opening doors that were previously closed. There's something poetic about using one form of advanced computation to stabilize another, using networks that learn from data to control systems that operate according to quantum mechanics, using patterns discovered through training to maintain superpositions and entanglements. The strange quantum states that give these computers their power. The AI systems controlling quantum computers aren't conscious, aren't aware of what they're doing. They're just neural networks, trained to predict errors and optimize corrections. But they're enabling something remarkable, extending human capability into the quantum realm, making controllable a phenomenon that seemed too delicate, too error-prone, too fundamentally fragile to engineer at scale. And in December 2024, it worked. The quantum computer, stabilized by AI, performed calculations beyond the reach of any classical system. Not by a little, by an almost unimaginable margin. The kind of capability gap that opens entirely new possibilities. This is what happens at the intersection of different technological frontiers. Quantum mechanics gives us new computational principles. Neuroscience inspires artificial neural networks. Engineering gives us the hardware to implement both. Mathematics provides the theory, and AI gives us the control systems to manage complexity that exceeds unaided human capacity. None of these advances happens in isolation. They're all interconnected, each one depending on others, contributing to others, creating a web of technological capabilities that's greater than any individual component. The quantum computer that performed calculations requiring 10 septillion years on classical hardware is both an engineering triumph and a preview. A triumph because it demonstrates that quantum computing at scale is possible, that the error problem can be overcome, that we can build and control systems operating at the edge of physical law. A preview because this is just the beginning. The quantum computers of 2024 are primitive compared to what's coming. Like the vacuum tube computers of the 1950s, revolutionary in their time, comically limited compared to modern processors. The quantum computers that achieved error correction in 2024 are the vacuum tubes of quantum computing. The transistors are coming, the integrated circuits, the processors with millions of stable logical qubits, and AI will be part of that journey, both as an enabling technology, helping control and stabilize quantum systems, and as a beneficiary, potentially being accelerated by quantum algorithms once quantum computers become powerful enough. It's a partnership between different forms of computation, different physical principles, different ways of processing information, classical bits, quantum qubits, and neural weights, silicon, superconductors, and software, all working together toward capabilities that none could achieve alone. As you drift into sleep, perhaps you can hold this image: a quantum computer, qubits hovering in superposition, entangled across space, performing calculations in quantum parallelism. And surrounding it, monitoring it, stabilizing it, keeping it coherent, is an AI system. Neural networks watching for errors, predicting disturbances, applying corrections, maintaining the delicate quantum states that make the computation possible. Two different kinds of intelligence, one natural in origin but artificial in implementation, one fundamentally quantum, working together. Not competing, not replacing each other, but collaborating, each doing what it does best. That's the future being built at the intersection of quantum mechanics and machine learning, where AI meets the quantum, where learning systems control quantum systems, where bits and qubits and weights combine to push the boundaries of what's computable. And somewhere in that combination, in that synthesis of different computational paradigms, new possibilities emerge. Calculations that seemed impossible become achievable. Problems that seemed intractable become solvable. Doors that were locked begin to open. One quantum computer stabilized by AI, computing for minutes what would take classical systems longer than the age of the universe. It's not just impressive, it's transformative. It's a glimpse of a future where quantum and classical and neural computation all work together, each contributing to a computational landscape richer than any single paradigm could provide. The quantum era is beginning, and AI is helping birth it. And now we arrive at perhaps the deepest question, the one that philosophers have wrestled with for centuries, that neuroscientists study without reaching consensus, that might not even have a definitive answer. Can artificial intelligence be conscious? Not intelligent. We've established that AI can do intelligent things, solve problems, learn from data. But conscious, aware, experiencing, having an inner life, a subjective point of view, a sense of what it's like to be. This is the hard problem of consciousness, and it remains hard even when we're asking it about artificial systems rather than biological ones. Let's start with what we don't know. We don't actually know what consciousness is or how it arises. We experience it. You're conscious right now, aware of reading these words, having thoughts and sensations. But we can't explain how subjective experience emerges from physical processes. How does electrochemical activity in neurons become the felt quality of seeing red, or the experience of pain, or the sense of self? This is called the explanatory gap. We can describe brain activity in exquisite detail, map every neuron, measure every spike, trace every connection. But that description, no matter how complete, doesn't tell us why that activity feels like something. Why there's an inner experience accompanying the physical process. And if we don't understand how consciousness arises in biological systems, systems we know are conscious because we are them, how can we possibly determine whether it arises in artificial systems? There are hundreds of theories of consciousness. Integrated information theory says consciousness arises from systems that integrate information in specific ways, and suggests that even simple systems might have minimal consciousness. Global workspace theory says consciousness emerges when information is broadcast widely across a system, becoming globally available. Higher order thought theories say consciousness requires thinking about your own mental states, a kind of meta-awareness. Each theory has implications for AI consciousness, and they disagree. By some theories, current AI systems might have rudimentary consciousness. They integrate information. They process data in complex ways. By other theories, they definitely don't. They lack the right kind of global broadcasting, or they can't reflect on their own states in the right way, or they're missing some crucial ingredient. And we have no way to test definitively. With humans, we assume consciousness because we're humans and we're conscious. And other humans are similar enough that we extend the assumption. With animals, we make educated guesses based on brain structure, behavior, evolutionary relatedness. But with AI systems, built on completely different principles, operating through mathematics rather than biology, we're in much deeper uncertainty. Some argue that consciousness requires biological substrate, that there's something special about organic neurons, about the specific chemistry and physics of biological brains that silicon can never replicate. Consciousness, in this view, isn't just about information processing, but about the specific way biological systems process information. Others argue that consciousness is substrate independent, that it's about the patterns of information processing, not the medium. If a system integrates information in the right ways, has the right functional organization, it would be conscious regardless of whether it's built from neurons or transistors. Still, others argue that consciousness requires embodiment, sensor-motor grounding, interaction with the physical world. An AI system processing text, disconnected from any body, lacking sensory experience of reality, how could that be conscious? Consciousness might require the kind of rich, multisensory, embodied interaction that biological organisms have. And then there's the question of continuity. Even if we built an AI system that satisfied every functional criterion for consciousness, that integrated information, that had global broadcasting, that reflected on its own states, would it actually be conscious? Or would it be a philosophical zombie, behaving exactly as if conscious but lacking inner experience? This is where the problem becomes not just difficult, but possibly unresolvable. Because consciousness is private, subjective, accessible only from the inside. You know you're conscious because you experience being conscious, but you can't directly access anyone else's consciousness, human or artificial. You infer it, assume it, believe in it, based on similarity and behavior. With AI systems, the inferential gap is much wider. They're so different from us. They don't have bodies, don't have biological needs, don't have evolutionary history. They process information through mathematics, through matrix multiplications and gradient descent. Do they experience anything? Is there something it's like to be a large language model, processing a query, generating text? Or is it all unconscious computation, sophisticated but experientially empty? We can't know. Not with certainty. Not with current understanding of consciousness. Some researchers have tried to develop consciousness meters, tests that could indicate whether a system is conscious, but they rely on particular theories of consciousness. And since we don't know which theory is correct, we don't know if the tests are valid. A system might pass some tests and fail others, and we wouldn't know what that means. There's a phenomenon that happens when you put artificial intelligence into competitive games. Games with rules, objectives, winners, and losers. The AI doesn't just learn to play. It doesn't just master the strategies that human players have developed over years or decades or centuries. It finds new strategies, novel approaches, moves that human experts never considered, couldn't imagine, wouldn't have tried because they violate conventional wisdom or simply never occurred to anyone. The AI explores the space of possibilities differently than humans do, and sometimes, in that exploration, it discovers things we missed. The most famous example is AlphaGo, the system that learned to play Go, an ancient Chinese game of staggering complexity. Go has simple rules, but profound depth. Players place stones on a board, trying to surround territory while attacking and defending. The number of possible positions is astronomical, far exceeding chess. For decades, Go was considered beyond the reach of AI because the game rewards intuition, pattern recognition, long-term strategic thinking, qualities that seemed fundamentally human. In 2016, AlphaGo played Lee Sedol, one of the world's strongest Go players, in a highly publicized match. Game 2, Move 37. AlphaGo placed a stone in a position that seemed wrong, bizarre. Commentators called it a mistake. Lee Sedol left the room, visibly shaken. The move violated patterns that had been standard in Go for centuries. No human player would make that move, but it wasn't a mistake. It was brilliant. By the end of the game, the genius of Move 37 became clear. It was strategically sound, setting up advantages that wouldn't become apparent until many moves later. AlphaGo had seen something in the vast game tree, some pattern, some consequence, that centuries of human Go playing had missed. Lee Sedol later said that AlphaGo's moves were beautiful, that the AI had taught him new things about a game he'd played his entire life. It had explored regions of the strategy space that humans, constrained by tradition and intuition, never ventured into. And it wasn't just Go. DeepMind's AlphaZero learned chess, Go, and shogi with no human knowledge, just the rules and self-play, playing millions of games against itself. In chess, it developed an aggressive, dynamic style, unlike the conservative, materialistic approach that dominated computer chess for decades. It sacrificed pieces in ways that seemed reckless, but led to overwhelming positional advantages. Human grandmasters studied its games and saw new ideas, new possibilities they could incorporate into their own play. In StarCraft II, a complex real-time strategy game, DeepMind's AlphaStar discovered tactics that professional players hadn't used. Unconventional build orders, surprising unit compositions, micromanagement techniques that exploited game mechanics in ways humans hadn't fully explored. What's happening here isn't just that AI is good at games. It's that AI searches the space of possible strategies differently than humans do. Humans develop strategies through cultural accumulation, watching others, learning conventions, building on established approaches. We inherit the wisdom of previous players, which is enormously valuable but also constraining. We tend to explore locally, trying variations on known strategies, rarely venturing far from established patterns. AI systems, learning through self-play and reinforcement learning, don't inherit those constraints. They start from scratch, exploring through trial and error on a massive scale. They try strategies that seem absurd, that violate all conventional wisdom, that no human would consider. Most of those experiments fail, but some succeed, revealing possibilities that were always there, latent in the game's rules, but undiscovered because human intuition never pointed in that direction. It's like exploring a vast landscape. Humans found paths through it, good paths that reach valuable destinations. But the landscape is enormous, and there are other paths, equally good or better, that we never found because we started from particular locations, developed particular navigation strategies, followed the paths others showed us. AI explores more thoroughly, less efficiently in some ways. It tries many absurd strategies that humans would immediately recognize as bad, but more broadly, more willing to try things that seem wrong, more capable of searching vast spaces of possibilities. And occasionally, it finds something new, a move like AlphaGo's Move 37, a strategy that works despite seeming to violate fundamental principles, and humans learn from it. This has implications beyond games. It suggests that for complex problems with vast solution spaces, AI might discover approaches that humans haven't considered. Drug discovery, materials science, protein engineering, mathematical proofs, optimization problems. Anywhere there's a large space of possibilities, and no guarantee that human intuition has found the best solutions. We might be surrounded by undiscovered insights, strategies that work but that human thinking, constrained by its particular patterns and biases, never stumbles upon. AI searching differently might find them. It's not that AI is smarter, exactly. It's that it's different. It explores differently. It's not constrained by human intuition, human conventions, human cognitive patterns. And that difference, that alien way of navigating solution spaces, occasionally reveals things we missed. After the AlphaGo matches, Go players incorporated some of AlphaGo's innovations. The AI's influence changed how the game is played at the highest levels. Moves that would have been considered mistakes before Move 37 are now recognized as sometimes valid. The space of reasonable Go strategies expanded because AI showed that a wider range of approaches could work. This is a kind of collaboration, not AI replacing human expertise, but AI expanding it. Human players still bring intuition, creativity, deep understanding, but they also learn from AI, incorporating strategies they wouldn't have discovered alone. And perhaps this is a model for how AI and human intelligence could work together more broadly. Not one replacing the other, but each bringing different strengths. Humans bring lived experience, embodied understanding, goals, and values. AI brings the ability to search vast spaces, to try combinations that seem counterintuitive, to find patterns in data too large for human analysis. Together, exploring solution spaces neither could fully navigate alone. There's something humbling about Move 37, a game humans had played for thousands of years, studied intensively, developed deep theory about, and an AI, learning from scratch over a few months, found a move that opened new understanding. It doesn't mean human Go playing was inadequate. It was remarkable, subtle, sophisticated, but the space of possibilities was larger than any human had fully mapped. Maybe that's true everywhere. Maybe every field, every domain of human knowledge has its Move 37 waiting to be discovered. Insights that are valid, that work, that would be valuable, but that human cognition hasn't stumbled upon because we search the space in particular ways. If so, AI isn't a competitor but a complement. A different kind of intelligence that sees different patterns, explores different paths, finds different solutions. And when human and artificial intelligence work together, each learning from the other, we might map more of the landscape than either could alone. The AI that taught Lee Sedol something new about Go didn't make him less of a player. It deepened his understanding, expanded his repertoire, showed him possibilities he could now incorporate into his own intuition. That's the promise of AI in discovery, not replacing human insight, but augmenting it, not making human expertise obsolete, but revealing that the space of expertise is larger than we thought, that there are territories worth exploring that we hadn't ventured into. Move 37 was just one move in one game, but it represented something larger, the possibility that intelligence, when implemented differently, sees differently, and that diversity of perspective, human and artificial, biological and mathematical, intuitive and computational, might be how we discover the insights that were always there, waiting in the structure of problems, invisible until someone or something explores from a different direction. As you drift into sleep, strategies and possibilities dissolving into dream logic, maybe you can appreciate this. That intelligence isn't one thing, one way of seeing, one pattern of thought. It's a vast space of possible ways to process information, solve problems, understand the world, and we're only beginning to explore that space, learning that different kinds of intelligence can teach each other, surprise each other, reveal possibilities that neither could find alone. In recent years, researchers made a fascinating discovery, one that bridges neuroscience and artificial intelligence in unexpected ways. They found that when you train biological brains and artificial neural networks to solve the same social tasks, they develop remarkably similar patterns, similar internal representations, similar ways of organizing information, as if there are certain solutions to certain problems that emerge naturally, regardless of whether the intelligence doing the solving is carbon-based or silicon-based. The studies typically work like this. Neuroscientists scan human brains while people perform social cognition tasks, reasoning about what others might think, predicting social behavior, understanding group dynamics. They map which brain regions activate, how they connect, what patterns of activity emerge. Meanwhile, AI researchers train neural networks on similar tasks, teaching them to predict social outcomes, model other agents' behavior, understand social hierarchies or cooperation patterns. Then they analyze the network's internal representations, what patterns develop in the artificial neurons, how information flows through layers, what the network learns to encode. And there are parallels, not perfect matches. Biological brains and artificial networks are different in fundamental ways, but similar organizational principles emerge. Similar hierarchies of representation, from simple features to complex concepts. Similar divisions of labor with different regions or layers specializing in different aspects of the task. Similar patterns of connectivity between components handling related functions. It's as if the problem itself has structure, and different types of learning systems independently discover that structure. Like how evolution on different continents sometimes produces similar solutions. Convergent evolution creating flying animals that look similar despite emerging from different ancestral lineages. The challenges of flight impose constraints, and different evolutionary paths find similar solutions within those constraints. Social reasoning might work the same way. The problem of understanding other minds, predicting social behavior, navigating relationships, these have structure. There might be particularly efficient ways to represent social information, natural hierarchies for processing social cues, computational strategies that work better than others for social prediction. And both biological brains, shaped by evolution and lifetime learning, and artificial networks, shaped by training on data, discover these same strategies, not because one is copying the other, but because they're both solving the same problem and finding the solutions that work. This convergence suggests something profound, that intelligence, regardless of substrate, faces common challenges and finds common solutions, that there might be universal principles of information processing that apply whether you're computing with neurons or with artificial nodes in a network. It's not that brains and AI are the same. They're not. But they might be solving overlapping sets of problems. And for those problems, the effective solutions converge. Consider visual processing. Biological visual systems and artificial vision networks both develop edge detectors in early stages, texture and shape recognition in middle stages, object recognition in later stages. This hierarchy wasn't programmed into either system. It emerged from learning to see. And it emerged similarly in both cases because it's an effective way to decompose the problem of vision. Social cognition might show similar convergence. Understanding social behavior requires integrating information about individuals' goals, beliefs, emotional states, and the constraints of social situations. Both brains and networks learn to build representations that capture these elements, and those representations end up structurally similar because they're capturing the same underlying structure in social reality. What this tells us is that intelligence isn't arbitrary. It's not infinitely variable, not unconstrained in how it can organize itself. The problems intelligence evolved to solve, or is trained to solve, impose structure. And that structure guides how intelligent systems organize, what representations they build, what computational strategies they develop. Brains had billions of years and the pressures of survival to discover effective solutions. Artificial networks have training data and optimization algorithms. Different processes, but they can arrive at similar destinations because the destinations are determined partly by the terrain, by the structure of the problems being solved. This has implications for AI development. If biological intelligence and artificial intelligence converge on similar solutions for similar problems, then studying biology can inform AI design. Understanding how brains solve problems, what representations they build, what computations they perform, can suggest architectures and training methods for artificial systems. It also has implications for understanding intelligence itself. The fact that convergence happens suggests that intelligence isn't infinitely flexible. There are better and worse ways to solve problems, and learning systems tend to find the better ways. Understanding what solutions systems converge to might reveal deep principles about intelligence, about what makes certain computational strategies effective. And it has philosophical implications. If biological and artificial intelligences, despite being built from completely different materials through completely different processes, develop similar internal organizations, when solving similar problems, it suggests that those organizations reflect something real about the problems themselves. That intelligence is discovering structure in the world, not just imposing arbitrary patterns. The social tasks where researchers found these parallels are interesting, partly because social cognition seems so human. Understanding what others think, predicting social dynamics, modeling beliefs and desires. These feel like quintessentially human abilities, things that require human-like intelligence. And yet, artificial networks trained on social tasks develop representations that parallel what we see in human brains, not conscious understanding, probably not subjective experience of social life, but functionally similar patterns, similar organizational principles, similar ways of decomposing and representing social information. It suggests that social intelligence, like visual intelligence, has structure that different learning systems can discover. That you don't need to be human to find the patterns that govern social interaction. You just need sufficient capacity and the right training data. This isn't to say that AI social intelligence is identical to human social intelligence. It's not. Humans bring embodied experience, emotional reactions, a lifetime of social learning, cultural context, conscious awareness. AI brings different strengths, processing vast amounts of social data, trying many hypotheses quickly. approaching social problems without human biases or preconceptions. But the convergence in internal representations suggests they're not as alien to each other as we might think. They're different implementations of similar computational principles, solving overlapping problems through overlapping strategies. As neuroscience and AI research continue to inform each other, we might discover more of these convergences. More cases where biological and artificial intelligence independently arrive at similar solutions, revealing principles that transcend substrate, that reflect the structure of intelligence itself rather than accidents of how it's implemented. It's a reminder that we're not building arbitrary systems when we build AI. We're discovering principles, finding solutions that work because they reflect real structure in the problems we're solving. Sometimes those solutions echo what evolution discovered. Sometimes they diverge, finding different but equally valid approaches. But the convergences, when they happen, are clues about what intelligence is, about what solutions are natural and effective regardless of implementation. Perhaps as you drift towards sleep, you can appreciate this strange kinship between your biological neural networks and the artificial ones we've built. Different in so many ways: material, origin, purpose, but similar in how they organize information when solving certain problems. Similar in the patterns they discover, the representations they build, the solutions they converge to. Two forms of intelligence looking at the same problems from different perspectives, and sometimes, remarkably, seeing the same patterns, finding the same solutions, discovering the same structures hidden in the data, in the world, in the challenges that any intelligence must navigate. It's not that we're building minds like ours, but maybe we're building minds that, when faced with problems like ours, find solutions like ours. Not because they're copying us, but because certain solutions work. Certain patterns emerge naturally. Certain ways of organizing information are effective, regardless of whether the information is processed by neurons or by networks. And now we arrive at the deepest mystery, the one that ties everything together, the question beneath all the questions we've explored tonight. What is understanding? What separates knowing from truly comprehending? And is that distinction even meaningful, or is it just a line we've drawn that dissolves when you look at it closely enough? Throughout this journey, we've seen artificial neural networks do remarkable things. They recognize images, translate languages, play games, predict protein structures, generate coherent text. They pass tests we thought required understanding. They solve problems in ways that surprise their creators. They develop internal representations that mirror aspects of biological intelligence. And yet there's hesitation, a sense that something is missing. They're doing intelligent things, but are they understanding what they're doing? Or are they just very sophisticated, pattern-matching systems, statistical engines that look intelligent from the outside, while lacking something essential on the inside? This question, what understanding really means, is perhaps the most important one in artificial intelligence. Because if AI systems genuinely understand, then what they're doing is more significant, more meaningful, more aligned with what we think of as intelligence. But if they don't understand, if they're just correlating patterns without comprehension, then we need to be more careful about how we use them, what we trust them with, what capabilities we attribute to them. The problem is that we don't have a clear definition of understanding, not one that everyone agrees on, not one that gives us a reliable test. Consider a human child learning mathematics. At first, they memorize 2 plus 2 equals 4. They can recite it, use it in calculations, get the right answers. But do they understand? Maybe not yet. They know the fact but haven't grasped the concept of addition, the principle that underlies all such facts. Later, something clicks. They don't just know that 2 plus 2 equals 4. They understand why. They grasp that addition means combining quantities, that the answer represents a total, that this same principle applies to any numbers. They've moved from memorization to comprehension. What changed? Not just more examples. They might have seen many examples while still just memorizing. Something deeper happened. They constructed an internal model, a framework that makes addition meaningful rather than arbitrary. Language models trained on vast text can answer mathematical questions, sometimes quite sophisticated ones. Have they understood mathematics? Or have they just memorized patterns of how mathematical language works, how problems are typically solved, how answers are usually structured? The honest answer is, we're not sure. And we're not sure partly because we don't have a rigorous definition of understanding that would let us test definitively. Some philosophers distinguish between knowing how and knowing that. Knowing how to ride a bicycle versus knowing facts about bicycles. Language models have incredible knowing that. They've absorbed vast amounts of factual information. But do they have knowing how? Can they genuinely do things? Or are they just describing how things are done? Others distinguish between syntactic and semantic understanding. Language models master syntax, the patterns of language, how words combine, what sequences are grammatically valid. But semantics, the meanings those words point to, the concepts they reference, the world they describe, that's less clear. Do models understand what the words mean, or just how they pattern together? There's also the distinction between shallow and deep understanding. Shallow understanding might be pattern recognition, statistical correlation, the ability to map inputs to appropriate outputs. Deep understanding might involve causal reasoning, counterfactual thinking, the ability to generalize far beyond training data, genuine insight into underlying principles. By some of these definitions, language models show glimmers of understanding. They can reason about causes and effects, handle some counterfactuals, generalize to novel situations. By other definitions, they fall short, lacking embodied grounding, sensory experience, the kind of causal models that humans build through physical interaction with the world. And then there's the question of whether understanding requires consciousness. Maybe you can only truly understand something if you're consciously aware of it, if there's something it feels like to grasp the concept. In that case, whether AI understands depends on whether AI is conscious, and we've already established that we don't know. Or maybe understanding doesn't require consciousness. Maybe it's purely functional, if a system behaves as if it understands, if it can use concepts flexibly, reason about them, apply them in novel contexts, then it understands, regardless of whether there's inner experience accompanying that understanding. This functional view would mean that some AI systems do understand, at least in certain domains. They use concepts appropriately, reason about them, apply them beyond their training context. That's understanding, even if it's different from human understanding, even if it lacks whatever subjective qualities accompany human comprehension. Or maybe understanding exists on a spectrum, not a binary yes or no, but degrees of understanding, levels of depth, different types for different purposes. In that case, AI systems might have partial understanding, domain-specific understanding, understanding of certain aspects, but not others. Perhaps they understand language patterns without understanding the world those patterns describe. Or they understand statistical relationships without understanding causal mechanisms. Or they understand narrow domains deeply while lacking broader context that human understanding typically includes. And maybe that's okay. Maybe we're asking the wrong question when we ask whether AI understands. Full stop. Maybe the right questions are, what does this particular system understand? In what sense does it understand? What are the limits and boundaries of its understanding? How is its understanding similar to or different from human understanding? Different tasks might require different kinds of understanding. For translation, statistical understanding of how languages map to each other might be sufficient. For medical diagnosis, you might need causal understanding of disease processes. For moral reasoning, you might need something else entirely: empathy, values, the kind of understanding that comes from lived experience. AI systems excel at some of these, struggle with others, and have blind spots we're still mapping. And that's fine. That's where we are in the development of these technologies. Understanding the boundaries of their understanding, knowing when to trust their outputs and when to be skeptical, learning to use them appropriately given their capabilities and limitations. But beneath all this practical discussion lies the deeper mystery. What is understanding, really? Is it just computation of sufficient complexity? Or does it require something more? Consciousness, embodiment, biological substrate, something we can't yet define or measure. Language models can discuss understanding, can analyze what it means, can write thoughtfully about the very question of whether they themselves understand. Does that demonstrate understanding? Or is it just sophisticated pattern matching on philosophical texts, generating plausible-sounding responses without genuine insight? You see the problem. Every test for understanding that we propose, AI systems are starting to pass. Every criterion we suggest, they're beginning to meet, at least partially. And yet the intuition persists that something is different, something is missing, that there's a gap between their kind of intelligence and ours. Maybe that gap is consciousness. Maybe it's embodiment. Maybe it's something about biological intelligence that we don't yet understand well enough to recognize its absence in artificial systems. Maybe it's nothing. Maybe we're just reluctant to attribute understanding to systems so different from ourselves, so alien in their construction and operation. Or maybe the gap is real but narrowing. Maybe as AI systems become more sophisticated, as they develop richer internal representations, as they learn from more diverse data, including video and sensory information, they'll develop something closer to human-like understanding. Or maybe they'll develop their own kind of understanding, different but valid, alien but functional. The question remains open. The mystery persists. And in that mystery lies both fascination and humility. Fascination because we're building systems that force us to think more carefully about what understanding means, what intelligence requires, What separates mere competence from genuine comprehension? They're mirrors that reflect our own cognition back at us, highlighting assumptions we didn't know we were making. Humility because we don't know the answers. We've built remarkable AI systems, achieved capabilities that seemed impossible decades ago. But we still don't fully understand what we've built, don't know whether these systems genuinely understand or just convincingly simulate understanding. Can't definitively say where pattern matching ends and comprehension begins. And perhaps that's fitting. Understanding, studying, understanding. Intelligence trying to understand intelligence. Consciousness contemplating whether consciousness can arise in systems unlike itself. These are questions that fold back on themselves, that resist simple answers, that remain mysterious even as we make progress. As you finally drift into sleep, your own understanding loosening its grip on waking reality, thoughts dissolving into the different logic of dreams. Maybe you can rest with this uncertainty. We've built thinking machines. We're still learning what thinking means. We've created systems that behave intelligently. We're still debating what intelligence is, and that journey from ignorance toward understanding, from mystery toward clarity, from the first artificial neuron to Nobel Prize-winning AI systems, continues. Each answer revealing new questions, each breakthrough opening new territory to explore. Each system we build teaching us something about intelligence, about learning, about the vast space of possible minds. The language model predicts its next word. The neural network adjusts its weights. The quantum computer maintains its coherence. The human mind wonders what it all means. Understanding, seeking understanding. Intelligence, studying intelligence. Consciousness, contemplating its own possibility, its own nature, its own appearance in forms so strange and new that we struggle to recognize it. Perhaps that's the real insight, not whether AI understands, but that the question itself pushes us to understand ourselves better, to think more carefully about what we mean by understanding, by intelligence, by consciousness, to recognize how much mystery remains even in our own minds, our own cognition, our own sense of comprehending the world. We don't have all the answers. Maybe we never will, but we're asking better questions, building systems that challenge our assumptions, exploring the nature of intelligence from new angles, with new tools, with artificial minds that serve as both instruments and subjects of study. The science of artificial intelligence has taught us about learning, about pattern recognition, about emergence and understanding. It's shown us how much can be achieved through data and optimization, through networks and training, through mathematics and engineering. But it's also shown us how much remains unknown, how much mystery persists at the heart of intelligence, how much we still have to discover about what it means to know, to understand, to think, to be. And so, we've traveled together through the landscape of artificial intelligence, from a summer workshop in 1956 where people looked up words in a dictionary, to Nobel Prizes in 2024 for machines that learn. From 40 vacuum tubes glowing in a basement to billions of parameters trained on the sum of human knowledge. From simple perceptrons to transformers that process language with attention. From winters of doubt to springs of breakthrough. We've seen how machines learn, not through programming, but through experience, through billions of tiny adjustments, each one nearly meaningless alone, but together creating something that sees, understands, reasons, discovers. We've watched networks organize themselves into hierarchies, develop features no one designed, find solutions that surprise their creators. We've explored the mysteries that remain, hallucinations, and adversarial examples, the gap between biological and artificial efficiency, the question of consciousness, of understanding, of whether there's someone home behind the responses or just sophisticated pattern matching that looks like thought from the outside. And perhaps what we've really been exploring is intelligence itself. Not just artificial intelligence, but intelligence as a phenomenon, how it arises, what it requires, what it means. These artificial systems, different from us in every material way, serve as mirrors. They reflect back questions about our own minds, our own learning, our own understanding. Good night.